1, 2, 3. Welcome to JuliaCon. All right. Cool. So okay, so we got a nice crowd here. And today what we're going to be talking about is Modeling Toolkit. So I just want to get a feel for the room. Awesome! We're now standing room only. We're officially. All right, cool. So for the room, so how many people here are familiar with Julia? And you said like you're a Julia user. You, thank God, you Julia. All right, we got the experience through here. All right, so how many of you are SciML users? You use differential equations, right? All right, cool. A few less hands, which means that there's some folks in here that just want to kind of learn what's going on. That's cool. Now, how many folks in here are actually users of Modeling Toolkit in particular? All right, so about half. Yeah, that's kind of what I expected, right? Because Modeling Toolkit is one of the newer things within SciML. And so it's not as used as, some of the other pieces. And also it's a bit more specialized, right? But what I want to talk about today, what I want to show you is all the cool things you can do with the symbolic numeric stack. And why I'm focusing us on specifically the symbolic numeric modeling toolkit tools as our way forward in a lot of the things that we're doing in SciML, right? Because there's a lot of things that we can actually do with symbolic numerics that we cannot do with purely numerical solvers. And I want to kind of walk you through how you build models as a way to then kind of show you, so the purpose of this workshop is multiple. A is to give you a bunch of ideas of like, Julia is cool because of the modeling toolkit, and you want to share Julia with other people, but you absolutely no idea what modeling toolkit does. Well, you'll learn at least enough about it to be able to share that, right? But the second thing is, you've been seeing all this symbolic stuff going on. You go, I use differential equations. I see all this symbolic stuff going on. Should I care about it, right? The answer is probably yes. But if you haven't figured out why it's yes yet, well, welcome to the workshop, right? And then the third reason is if you actually want to build these industrial models, right? So industrial modeling requires to get different people from different expertise, right? You'll see that tomorrow we'll have a keynote talk with someone from Boeing, right? And we've been working a lot with folks from Instron and all these other, all these other communities where people are building, trains, airplanes, cars, and everything using Julia tools. But the key thing is when people do these realistic models, they don't build every single model from scratch, right? You have your specialist that knows how HVAC systems build an HVAC system. Your specialist who knows how to build a battery builds that. The specialist in vehicle dynamics builds a car model. And you should be able to just plug all of your models together and generate a composed model, right? Building that composed model by hand using differential equations.jl correctly, it's in theory possible, but in practice, you'd actually have to kind of know all sheet equations, right? So if you're in this distributed world where a lot of people are now working together in this big industrial environment, how do you actually build these large systems where no single person is truly an expert on the whole thing, right? And that's what Modeling Toolkit is really a tool that's designed to be used for. And this is this hierarchical component-based modeling. So we'll get there. But again, we're going to get to the hierarchical component-based modeling part, but we're going to go through a story. And that story is going to first start out with symbolics. We're going to talk about, what Modeling Toolkit is used for, and I get this great overview before really walking into how we're going to use Modeling Toolkit for building out these higher, larger models, right? Now, in this specific workshop, I will not be giving you examples of huge models. Why is that? Well, because generally, if you have a huge model, it's going to take a minute to run or whatever, and, we don't have time for that, right? So, but what we will do is I will show you how to build these hierarchical models, and I'll use some example systems to be able to explain what is going on so that we can sort of take this on your own. But that does not mean that this content is not here at JuliaCon, because a lot of folks from Julia Hub have been building these component models, like digital twins of batteries, digital twins of HVAC, etc. And I think that there's about 12 or 14 other talks at this JuliaCon which are dedicated to high-fidelity simulations of a specific modeling domain. And so hopefully this will give you an understanding of, here's how people build modeling toolkit libraries, here's how you use modeling toolkit libraries, and then these other talks will go into detail about specific application areas where people have been building these libraries for you to be able to make use of. So that's my quick introduction about why you want to be here, if you had no idea. But the starting point is modeling toolkit feature, not sale. So what the heck is modeling toolkit? And let's start there so that way we have a basis, right? And the key is that it's really built around industrial modeling and simulation. It's really about being able to make it so that this modeling process can scale. So what does that mean? So the way that I'm going to do this workshop is I'm going to introduce you to words, like things like Acausal modeling, which will at first make no sense. I'll give you one explanation and you'll be like, I did not understand what Acausal modeling is, right? I'll give you the second explanation, and you might still not know what it is. I'll give you a third explanation, a fourth explanation. If we repeat this a few times in different ways, I think that it'll start to come together what's going on, right? So at first, I'm going to tell you, like, oh, it's Acausal component-based modeling. But what you do is you take these things, like, for example, you have a model of a spring, you have a model of camber, you have a model of your inertial elements, and you connect them together, and what it does is it builds a differential equation behind the scenes. And then you go, I don't understand how it's building that differential equation. Don't worry, because we'll go into copious amounts of detail about how that's working, right? But the idea is that you can do this with mechanical systems, with electrical systems, with thermal systems. You do this with the magnetic system, and all types of systems. Actually, anything that goes off of that Hamiltonian, anything physical, fits into this Acausal modeling framework. And then the next thing about Acausal modeling is that it makes it very easy to be able to reuse physical components, right? So if someone has designed the physics of a real world, you have a capacitor that has, heat loss, due to, for charge loss due to heat and all this extra kind of physics involved with it. If they really strictly model this thing, you can just say, okay, I have a capacitor here, let me just plug yours in and generate the larger differential equation. So the core of Acausal modeling is it makes it very easy to reuse a lot of the other work that people have done, and you'd be able to build these libraries of real physical components, right? And so Modeling Toolkit, it is heavily inspired by something that is called Modelica. If you've never heard of Modelica, that's okay. If you have heard of Modelica, then this is an introduction slide that says, oh, this is very similar to Modelica. But then again, if you haven't heard of what Modelica is, then that's not going to be familiar yet, right? But this just to give you an idea of what these models kind of look like, right? So the models, this is the model that's being built as the RC circuit, where we say, you have these components, right? These things these physical models that someone else has built. You take these physical models and you say, I connect out of these physical models, and then I build it, and at least this part should look very similar to every one in this row, right? I build an ODE problem, I plot it, I solve it, all this stuff, then it becomes standard differential equations. So the key is that this is basically a symbolic modeling layer that goes before differential equations. That is all just a way to be able to specify what kinds of differential equations we're going to end up solving, right? And again, the core point of it is that it allows you to have someone be able to build these individual components, and then a full model is just stitching together many different components that people have built in standard libraries, in your own libraries, and everything else. And there's a growing list of these libraries. Again, many of these will have their own JuliaCon talks. I can see the folks in here that was talking about the process modeling talk, and people would be talking about fluid models. I think the aerial vehicles person, I didn't see him walk in here, but I need to have to show up. We're going to have multibody systems. I think actually we don't have a talk on multibodies this year, but that'll probably be next year's JuliaCon. Battery systems, Sebastian will be giving that over there. HVAC systems, Avinash is in the audience up there. I just saw him as well. And so there's all these different types of domains, right, where you say, okay, I want a realistic system that is, HVAC system. I want to plug it into electric vehicle to understand what is the power drain of a Tesla on this battery. And if I change the battery to a new chemistry, how will that change the thermals of the battery, right? And it turned out that building these, hundreds of thousands of differential equation models, you can do this in like 20 lines of code just by stitching together these pre-made model libraries, right? So this basically gives you a whole system where you can do this kind of process of model building, but you can distribute it, right? And there's a lot of really nice examples that we've been building with here. I'm just building something from JuliaHub. So we had Brad Grubman will be giving the lunch and learn on JuliaSim. He was one of our very early users of Modeling Toolkit, right? The first JuliaCon workshop or first JuliaCon talk in Modeling Toolkit was in 2020, and then summer of 2020, this guy was using it. So very, very bold move right there. But it ended up working out for him because what ended up happening was he was using Simscape before, or some other modeling software by some folks that made some other thing that rhymes with SatLab, right? And what happened was that I was able to get something that performed over 1,000 times faster than this modeling software that was able to really build out something that would be able to optimize this real world system, right? In fact, it was able to model it so well that they were able to understand that you didn't actually need these two pistons to be able to cause this car to move. You can actually model it with one of these pistons, and if you have effective unmodeling and simulation, you can actually control it so well that the one can act as the two, right? And so there'll be a whole story if you want to understand, all the different case studies and such. We have a Julia Sim lesson learned where folks will be going into a lot more detail about these examples. But I just want to kind of give a quick introduction to say there's a lot of real world use cases that are now being built up in the industrial sense around Modeling Toolkit and its uses.
Just a quick question.
Yes.
We'll have to make sure that we are recording.
Are we recording? Yes. I mean, I was told that the recording is not done from my side, that someone else is. It is
recording, so we're good. Thanks.
So, all right. Coolio. All right. And so if you also are doing all these things in the scientific machine, so how many people here, I guess, are interested in the scientific machine learning aspects, integrating neural networks in with the different equating modeling? And curious. Okay, cool. So there's a lot of people who are interested in that aspect of SciML. I mean, it is in the name, right? And so this is actually something you do with Modeling Toolkit as well, where what you can do is you can say you build up this system of all these different components, but you might know that, hey, this one component, I modeled my fluid using the ideal gas law, but the ideal gas law is very inaccurate for things that are not ideal. So I can have the neural network inside it there, and boom, you now have this kind of form where you have a digital twin where you say, I know some things, I don't know some things, and you learn the components and you learn improvements to the components that you did not know, right? So the same SciML workflow does actually work even within this context of Modeling Toolkit. This is actually a recent addition because for a while we've had these as two separate worlds, the SciML verse and then everything that worked in Modeling Toolkit, which within the last 3 months we've gotten the neural network integration completed. So, yeah, we finally got this all together. I won't be demonstrating that, but that will probably be a future JuliaCon talk. And if you're interested in making use of a lot of these in the industrial setting, I do have to give a shout out to the Julia Sim, which we've been building on top of Modeling Toolkit, which is a bunch of tools like graphical user interfaces and these kind of more sophisticated model libraries for being able to really connect this into downstream deployments and real world industrial cases. So if you're interested in using Modeling Toolkit for industrial context, you might want to get in touch with us for some of the other things we've been building. Though there should be more that we'll be talking about with the graphical user interfaces on Modeling Toolkit in the near future. So that's Modeling Toolkit in a very, very, very quick nutshell. Again, I'm kind of going fast here because I want to get to the real coding sections. But so the next section is, this is very JuliaCon specific. Because as I thought, most people in the room are like, okay, on a Julia SciML use it, right? I use two different equations, I not really solve. I use these other tools. What can Modeling Toolkit offer to me, right? So maybe you're just at university. You don't care about someone's, high-fidelity HVAC system, but you do care about your own code, right? So why should you care about Modeling Toolkit? So the Modeling Toolkit, what we're going to be talking about in a specific workshop will just be on differential algebraic equations. But it turns out there's a lot of other systems that can understand and model using Modeling Toolkit, right? And so here, for example, is a system where I say, I have some differential equation, which I'm already super symbolically, but I also have a noise term. So, I add a Brownian term to this. And it knows that I turn this into something solvable by stochastic delay differential equations, right? And okay, but I could have written that stochastic delay differential equation by hand for stochastic delay differential equations, right? So why would I ever want a symbolic modeling layer involved? Doesn't that just make things harder on me, et cetera, et cetera, et cetera, right? Well, here's something that you might not have known about that would be very useful, right? So let's say you have a stochastic model. So here's Catalyst, which Catalyst is a domain-specific language which is built on Modeling Toolkit. You can already start to see some of these things, right? So, if you're building your own domain-specific language, well, you might want to target something that is able to generate the Jacobians, the Hessians, everything for you. And this is why Catalyst, for example, uses Modeling Toolkit. But here, for example, it's building a model. This model is some stochastic process, right? And you go, well, I can solve that with numerical tools. Why don't I just solve it 10,000 times? And this random process, I can get the mean and the variance. Well, it turns out that you can actually do something smarter, right? So it turns out that, so this stochastic process also has an approximating ODE, that is the mass action equations. And Modeling Toolkit knows how to take this stochastic process and automatically generate the approximating ODE. So it can say, here's an approximating ODE for the mean flow, right? And it's able to do that because it knows the symbolics of the system, and there's a way to calculate that. In fact, there's something even deeper. So for one of these stochastic systems, you do this whole process, write out moments, et cetera, et cetera, et cetera. And after you do this moment expansion, you can then say, oh, hey, this stochastic process, this thing that has a random output, generate the ODEs for me, where the ODEs are the change of the mean, the variance, the third moment, the fourth moment over time, and then do a direct simulation of solving for what the means and the variances are, right? And so now instead of solving this stochastic simulation over 100,000 runs, you now solve one set of ODEs, which directly gives you the means and the variances, right? It's an approximation because of low exposure, but you can go to higher orders, et cetera, et cetera. But this kind of should help you kind of understand that, really, you might see these papers where someone said like, oh, like, hey, you could do this this core simulation, or you can do a lot of math to derive something else, and then you just like this, it gives you properties regional system, right? Anytime that anyone says you can do a lot of math to get a different kind of system, you can think about it as there's a symbolic transformation from system type 1 to system type 2, and I can automate that and then solve system type 2 and then give you what it looks like for system type 1 as an approximation, right? And this process of changing systems around, of transforming systems, that is the core of what ModelingToolkit does. The core of what ModelingToolkit is just a way of explaining to a computer what your mathematical systems are and how we should be transforming them into different ways to use different types of numerical solvers to exploit properties, right? And so you might have this gigantic stochastic simulation, which you can now simulate deterministically for the moments, and then that saves you a whole bunch of computing power. Right. There's all sorts of other things involved as well. So, for example, there's a whole PE interface, which we're not going to talk about in the rest of this workshop. Right. So there's a whole PE, partial differential equation interface, where what it does is it takes partial differential equations and generates ODE systems that are interpretable as the PE solution over time and space. Right. And so again, this is just a transformation, right? We're transforming a partial differential equation system into an ODE system representation, and then it gives you the way to be able to map back, right? So ModelingToolkit at the very core, and why it's useful to everyone who does both industrial simulation and people who do, academic work. It's useful as a system for transforming between different representations of solving. And there's a whole discussion to be had about this partial differential equation interface, but that's its own talk of its own. So then, so this tells you like, okay, if you have big models and want to be able to solve them, what you could do is you could sit down with a whiteboard and you can derive, how do I simplify my model? Or you could have a computational system automatically fix your model for you before you solve it. That sounds pretty nice. So ModelingToolkit is that. It's a system for transforming models into versions that are better for simulation. And so then what truly is ModelingToolkit, right? So it's this system for transforming, but let's start to make this a bit more concrete. So what ModelingToolkit is it's a way of mixing symbolics with differential equations, right? So the core behind it is, the way that we represent our differential equations now is instead of giving computer code, right? Instead of giving it mathematical function or computer functions, right? Computer functions have a lot of limitations in terms of the math that you can do on them. So instead what we say is giving the symbolic representation of what your equations are. So I know exactly what those equations are, right? And what we want to do is we want to know the symbolic representation of the equations to something that is calling the numerical differential equations, right? So ModelingToolkit is the step in between the two of those, right? The ModelingToolkit is the transformation layer from the symbolic representation of differential equations to generating the code that is then used for the numerical simulation. So here, this is already showing you certain things that might be useful. So for example, here I defined a second order ODE system, right? So there's a second order ODE here. But most of the ODE solvers only solve first order ODEs, right? So here what you do is you can say, oh, generate my ODE system, and now lower it to a set of first order equations and then solve it, right? And it can symbolically know how to generate the equations for first order systems, generate the code for that, solve it, and then map it all back. And what this means then is a symbolic so ModelingToolkit then is really built on symbolic.jl, which is then built on all these other tools, which has all the different types of simplification layers in there for Grosvenor bases, et cetera, right? And for the most part, we don't really need to know about how it's doing its simplifications, but there's a whole simplification process that is underlying under the hood, right? And so, so the core point of then what ModelingToolkit truly is that they system for symbolically defining. It's a system for symbolically defining mathematical systems like ODEs, nonlinear sets of equations, optimization systems, and then getting you stable transformations, right? So the point is that, going east or lowering, it's not just some step in a compilation process. It's something that takes in an ODE system and spits out an ODE system. So you could do other transformations, right? You could say, okay, now that I have an ODE system, I could, say, do a simplification on it. I could do a log scaling of some of my input variables, right? Because if you want to be able to ensure that your solution is positive, you might want to shape transform your equations into log space, right? All these kinds of things that you do by hand in order to prove the numerical systems, you can now do this all as steps in these transformation pipelines, right? So Modeling Toolkit is then all about these stable transformations on these systems, right? And it turns out that there's a lot of different ways you can make use of this for improving numerical code, right? So here I want to kind of just highlight, at the very beginning, why this might be useful to anyone that's doing numerics, right? So here's a nonlinear system, right? So the write down U1 minus sine of U5, U2 minus cosine of U1, right? Here's a nonlinear system of five equations with 5 unknowns, right? So if you were to take this today and send it to a numerical solver, right? If you use SciPy, you give it to Newton method, nonlinear solve.jl, Newton method. If you use anything in the entire world, you give it to a Newton method, right? Solve this by system. Now the system's not very large, so this will solve quickly, right? But what if we had this very huge system of equations and all kind of look like, this form? What would we want to do? Well, does anyone know what the scaling of Newton's method ends up being? Newton method tends to scale like O of n cubed, right? So it scales much worse than linear, which means if we can spend any time to be able to get rid of equations, then we can save a whole lot of time, because as our equations grow, Newton methods grow and cost a lot. But can you see actually how you do this? Well, it turns out that if you solve this, you can say, U1 equals sine of U5, U2 equals cosine of U1, which is actually equal to cosine of sine of U5, et cetera, et cetera. If you spend enough time with these equations, you realize that you can actually transform this into just one equation, right? So there's just U5 equals a hypotenuse, U4, U1, where U1 could be defined as sine of U5, but you can plug this later recursively, you actually see that you get an equation only in terms of U5, right? So that means you actually only need to solve a nonlinear system in terms of one variable, and you need to reconstruct all of the other equations from that one variable, right? For U5, you get U1, for U1, you get U2, from U1 and U2, you get U3, from U2 and U3, you get U4. So you could do this by hand, right? You could do this by hand, right? Given all these equations, you can come up with how you would schedule this, and you can say, I don't actually need to solve this whole system. I could just solve one equation, right? But it turns out most people don't do this by hand, and so you lose a lot of performance, right? There's only so much performance a numerical method can give you if you actually wrote down this as JuliaCon, right? But a symbolic system can simplify it before it generates the code, and by doing so, it can save a lot of time. And now the key along the toolkit, though, is it's an interface on top of SciML. So if you already know how to use SciML, then all you have to do is you just start interacting with it symbolically. That's actually the work of the symbolic indexing interface, and there will be a talk specifically about all the details in the symbolic interface. But here's what happens, right? So I say, okay, I give it an initial guess, and I solve the nonlinear system. And you see, my 5 equation system, it tells me I got a solution revolving one variable. You're like, wait, what? How do I deal with that? Fine. But if you index the symbolically, say, give me the solution of U1, they'll give you it. If you give me a solution of U2, they'll give you it. So it solves the minimal system that it needs to, but if you then ask for all of your other variables, then it knows how to reconstruct those. Now, importantly, though, again, Newton's method scales like cube, whereas these are all linear sets of equations, or these are all basically like O of 1, or So the cost of doing it in this form, where you first simplify before doing the solve, and then the reconstruction using explicit equations is much, much cheaper than it is to be able to do it all directly. And so Modeling Toolkit then, if you might run into this a lot if you're a user, because Modeling Toolkit has become somewhat of a target for a lot of different domain-specific languages, right? So you might see that, for example, based Modelica.jl, so for people who are writing these development writers, well, how should you give people the system? You don't want to just give them direct Julia. You want to give them somebody that can understand the system well. And so based Modelica gives you Modeling Toolkit code. Kumas, if they understood, use Modeling Toolkit. Catalyst, which is for biological systems, gives you Modeling Toolkit, which also means that the SciML readers, it's SciML files, which is a file format used in computational biology. SciML, which is a file format used in physiology, right? All of those read as modeling toolkit. So at the end of the day, a lot of different types of systems end up just giving you modeling toolkit systems, right? Because if you read a file, it gives you then at the end of the day on these systems, so that way you can go be your own transforms and use it, right? So modeling toolkit then, you will see it a lot in the Julia ecosystem because it's kind of a target format for a lot of other forms of tools. And so I think that there's going to be some thoughts in capacity college and field talking about all the different domains. People are using modeling toolkit under the hood for these different systems. And so if you did want to say interact with computational biology and such, you will find that modeling toolkit is that interchange format that everyone is using there, right? So what does modeling toolkit do for the performance of difficult models, right? I do want to highlight so this is a piece that has been recently created by a Julia group. And so I just want to highlight some of the nice features that we have so basically modeling toolkit has this way of doing structural simplification and doing these simplifications, right? But we actually have a alternative compiler that is built around more around the scaling aspects. It's free for academic use. And what you do is you just add it to the simple compiler and you turn your system into an IR system before structural simplification. So you literally just add two lines of code to your modeling toolkit code, and you can have alternative compiler paths which are optimizing in different ways. It turns out that this alternative compiler is really focused on scalability for large-scale models. So for things that are, say, integrating neural networks, for things that are these large partial differential equation things. And what it's doing is, if you have these kind of models where you say, I have n capacitors and resistors, right? What you want to do in this kind of situation is you don't want to. You want to be able to find that, oh, hey, there's this repeated structure to it. And because there's this repeated structure, what I can do is I can find, what a repeated class of structures, and then I can build a loop around it. And so you can then, with the code that it is all looped. And then it turns out and then the next question is, oh, can you do nice SIMD on it, et cetera, et cetera. And if you know the folks that do, loop vectorization.jl and JuliaCon and all these fast coding libraries, well, it turns out that the same people who build those libraries are also the same people who are building this compiler, so the code that's coming out of this is pretty ridiculously fast. It's actually writing directly to LLVM, which is why it's written in a weird way. But then the code they get so if you're just using direct modeling toolkit, and in the full symbolics, you have performance that, as you get to number of cells, so the number of cells has 300 equations per cell. So as you start to get to the level of 10,000 equations, purely symbolic forms tend to have, some overhead. But then there's these other forms that are able to scale to the millions of equation sizes. So modeling toolkit has this whole ecosystem that's growing around it. It has different types of compilers that are all interoperable, that are then able to give you different optimizations that are specialized to different types of regimes. And just to kind of highlight some more about what modeling toolkit is doing for performance, so here, one area where performance aspects come up a lot is if you work in things like robotics or multibody systems, right? And on robotics and multibody systems, what you'll find is that a lot of linear relationships are mixed in with non-linear relationships. And what these modeling toolkit compilers will do is it will find the linear subsets within your system, and then it'll directly embed some linear algebra in some smaller sparse linear algebra to be able to optimize all the structures within there. And that actually has a direct our OLE factorization that is a version of recursive LU that is written directly in LLVM by the same guy who wrote the Julia BLAS tools like JuliaCon and all that. And he's been writing this thing that basically just does the embedding of this linear solves, and that ends up being rather fast, right? And so there'll be other talks about those kinds of aspects. But these are things to then understand, right? That, if you were to write down these models by hand, you might not do all this optimization. You might not do these inline linear solvers, et cetera, et cetera. But modeling toolkit is a system that is built around, give me your equations and I will try to find out what to do with it. And again, we're still working on it in a lot of ways. And so the performance of the system continues to improve, day by day. The number of optimizations that we're adding to it are kind of growing. So, you really have to check out the repo to understand, which optimizations do we have and don't have, and what kinds of systems are fully optimized and which ones have optimizations coming in the near future, right? So that's the big overview of modeling toolkit. And now let's go into the start of the live coding section. So I'm going to see if I could put my notes up on the side here while I code directly next to it. And pray to sweet baby Jesus that that this all goes as smooth as I hoped. All right, cool. So, okay, and so if you haven't gotten the Flutter notebooks, great. Remember, you can get these Flutter notebooks by right here. You can get these Flutter notebooks by going to GitHub and you go to the GitHub SciML, right? And then you do a ModelingToolkit workshop _JuliaCon 2024, and hopefully, if we have not renamed it, that right there is where you're going to find those notebooks, right? So here I'm going to have this notebook, a little bit on the right. But I find that going through slides, everything is too fast, right? So let's then go step by step and really understand how to use the symbolics and modeling toolkit by walking through every step of this process. And how do I close the site editor? Usually it would close Command B. Yeah. All right, cool. All right, cool. So first things first, you got to load our libraries, right? So before you get to start talking about ModelingToolkit, remember ModelingToolkit is built on top of symbolics, and so it's good to understand Julia symbolic. Now, I asked a bunch of questions earlier about if people were into it. I had used before. How many people have actually used symbolics.jl? All right, so about a good half, yeah. So that's seems like it's about the same exact half as the half that had used ModelingToolkit before, which makes a lot of sense. Right. Okay. So let's pump this up a little bit. So let's do using symbolics. Right. Let's start by pulling in the symbolic library. Right. So the first thing first is how do you use symbolics? Right. So how do we do that? We just say at variables x y. Right. And now the key to so you might ask the question of what is a symbolic variable and how does that differ? How does a symbolic variable differ from a normal? Right. So normally the Julia variable or any variable in an imperative programming language does computations, right? The symbolic variables do not do the computations. Instead, what they do is they build up a graph of the computations that they are representing, right? So if you have your symbolic variables and you say x plus y, right? It's not actually going to do the computation x plus y. But it's going to build a representation of the symbolic expression that is x plus y, right? So what symbolic variables allow you to do then is build all these different expressions, right? And you can see, you have x plus y. I don't know why it really wants me to yield. I'm not yielding to no one. I'm American. So you can get x divided by y. And now if you're using Flutter notebooks, right? You'll see that I actually have a way to directly generate LaTeX, and so that will generate LaTeX of all these commands. And you can see they can make all sorts of commands, right? So you can say, okay, sine of x squared plus cosine of y squared divided by 2, right? There you go, and it builds this expression, right? It might move some pieces around and say, okay, it's actually one half of this or something, right? And you can distribute it and all that, right? But what it's going to do is it's going to find an equivalent representation of the underlying expression that you've written. Right? So, okay, cool. That's it. That's symbolics. But the purpose of this though is really multifold. So here's the key, right? So okay, I showed this on say sine, but does this work for your own function? So let's actually just show this. So I say my expression of xy is equal to square root of x squared plus y squared, right? And then I call my expression of xy, right? And so the key to this is that symbolics actually doesn't care if you define your own Julia function. It knows how to handle your Julia function by tracing. Now there is something called registration, so that way you can tell it how to handle new functions as coordinates. Right? Square root and power and such things are just defined as registered functions. So symbolics is completely written inside of Julia, and so any function that is specialized inside of there, you could specialize in your own session. The documentation goes into detail on how to do this, but the point is, there's nothing special about your functions versus functions that are built in. The library just handles them all the same, right? Because again, it's just purely built in Julia. But now there's a lot of other things you can do with this, right? So Julia is a full programming language. So what about building arrays, right? So here, this is an array of symbolic expressions. I just built an array, a Julia array that has symbolic expressions in there. You see what this says is the matrix of num. Num is the symbolic expression type. And so this is a matrix of symbolic expressions, right? And now you can say, well, okay, well, Julia is a full linear algebra programming language. So let's do something, but what's something that is hard to compute? Well, you say like using linear algebra, take the inverse of A, and well, there you go. It computes a symbolic representation of the inverse of A. And now you go, wow, how long did you come up with that cool example just to be able to do this? And it turns out, no, we actually didn't spend any time writing this because Julia has a code for doing the inverse of a matrix for numbers, right? The symbolic representation, num, says it is the subtype of number, and so it traces right through the number code to be able to give you this inverse of a matrix, right? So what this means is that if you have general codes that work on numbers, you can put symbolic representations in there and get a symbolic representation of that computation, right? And now here's a party trick. So I'm going to grab the ordinary differential equation solver. I'm going to say, I'm going to build a function that is my ODE. And I'm not going to explain how the ODE definition is done because everyone in the room here has stated that they've used ODEs before, right? So here I'm going to say, okay, here's my ODE. It's sine of x squared. I'm just going to define a scalar ODE, right? And now I'm going to say simprob is equal to ODE problem of my ODE and an x, where x is my symbolic variable. And then I'm going to do 0.01.0, right? And that says, like, okay, my zero, it doesn't have a number to it. Well, it has a number that is my initial condition. My initial condition is just a symbolic variable, right? And now I solve, and now I just say, my symbolic solve is equal to, solve my symbolic problem with RK4, and I do adaptive equals false because you can guess why adaptivity wouldn't be the nicest thing here. And then say that equals 0.1. And oh, I also need to give it a dt. You know what? Let me just do dt equals 0.1. And there you go. It's actually going to spend more time trying to print it than anything. So while it's trying to print that, well, what you can see here is that it will actually just trace through the ODE solver and give you the symbolic expression for what Rackauckas fourth order is doing on its 10th time step. Now, you never really want to do this, but this shows you that, yes, you can. Oh, God, this keeps going. The supertype of num is, I think it's actually real for the same reason that forward diff numbers end up being real, right? And so you can actually, so you can see that the simsol of n is actually this full expression, right? So now you might think that, oh, this is a cute party trick and it's not actually useful. Well, if you actually do things like optimal control, right? For example, where in optimal control, you want to be able to build out a representation of say, some Rackauckas expression, and you want to be able to generate a loss function with respect to that Rackauckas expression at a much different point in time. Well, if you don't actually want to write the Rackauckas expressions yourself, you could just call the ODE solver to give you the representation, and it already has all the Rackauckas tableaus and everything. So it turns out that this is a nice way to build some of these tools. I'm going to cut this because I think it's just going to spend forever just trying to print. But you can see that, it really just does give you a... Oh, no, it really is trying to print a lot. All right, well, I'm going to cut that in and just pull a few things back in. But you can see that, there's nothing special. I did not spend, a month or something making it so that the ODE solver works with symbolics. This just is a property that the ODE solver works on general numbers. The symbolic library, variable library, its thing works on numbers, so therefore you can generate these symbolic expressions, right? And you use these symbolic expressions anywhere you want symbolic expressions, right? So, okay, so that's how you get symbolic expressions, right? So you can get symbolic expressions by writing them yourself or generating them through tracing other number code. But how do you actually use it? Like, why would we want a symbolic representation? Well, one nice thing with symbolic representations is you can calculate derivatives, right? So let me recreate this, at variables x and y. So it's symbolics.derivative. So I can do x plus x squared. And I want to take the derivative of it with respect to x, right? And it says that the derivative of x plus x squared is 1 plus 2x. Boom, there you go. So symbolic derivatives, easy. Now, I want to kind of highlight here for a second how this is actually working, because some of this, the internals of here will actually show up now next in the way that we define differential equations, right? So the key is that, symbolic set derivative is a function, but if we want to actually represent the differential, like the derivative itself, d by dx as an operator, we need to be able to build that operator, right? So you can say, for example, that dx is the differential operator with respect to x, right? And you can then say dx of the differential operator applied to a function that is x plus x squared. And now this is the differential operator applied to that expression, right? And if you check it in LaTeX, maybe the LaTeX makes more sense. Maybe let me boost this up in case it's a little too small. Right? You can see from the LaTeX what this differential operator means. It means the expression d by dx applied to the x plus x, right? Now, you might go, well, why doesn't it compute the derivative? Well, because in many cases, you want to actually understand and represent the differential operation itself, right? So what's a case where you might want to do that? Well, differential equations themselves, you have to represent them using the differential operator. D by dt equals dy by dt equals, right? So you have to be able to express this differential operator. And so, what this is really going to showing that the differential operator is used for differential equation representations, but it's also the same exact thing that's used to compute symbolic derivatives. All we have to do is we then just put on top of this, we just say, expand the derivatives, and then it will expand out the operator's actions on equation, and it will generate the symbolic expressions, right? And now by here, because we have that x and y are just these constants, and we're just differentiating with respect to x, it knows that dx is 1, and to get rid of it. But the important thing here is that in symbolics, we can say, I have a variable like, z of x, right? So I have a symbolic variable that is a symbolic function, right? It is a function of x. In which case, if I do then, my deriv is equal to expand derivatives of d of x. If I now put this differential operator on x squared plus z squared, right? We can now no longer assume that dz dx is equal to 0, right? If we can't assume that, then that means we need to actually represent that the derivative of this expression is the chain rule, right? Two types of derivative of x. You have a dz dx, right? Yeah, so this is just that chain rule. It's in there, right? And so what this means is that if you as long as you declare your variable relationships appropriately, they'll keep everything involved. Keep all the chain rules. Because if you're say trying to do something like write down a Lagrangian expression and then generate the associated ODEs, you can actually just use the symbolic library itself as the process for generating the equations that are associated with your Hamiltonians, with your Lagrangians, and all these other representations, right? So there's not, so you'll find that, in Modeling Toolkit, we will use the differential operator, right? But there's nothing that is specific to Modeling Toolkit about the differential operator. It is actually just the operator from the symbolic library that is used for the derivative calculations, right? And so one of the things that we can do here is then you can say, okay, on this expression, right? Let's say I wanted to evaluate it, right? So you can always use substitution in order to do evaluation, right? So let me show you that substitute, because this is a trick that I will end up using a bit later in the talk. So the substitute function, right? Again, you can go to if you go to the symbolics documentation. So if you go to symbolics.jl, you'll find that it has a documentation that has, say, tutorials and all these doc strings and such. And so, for example, if you would actually look and you say substitute, how does this work? It'll give you examples on how it works and all, right? If anything doesn't have appropriate documentation, the proper thing to do is you just yell at me, and then I'll add the documentation wherever is needed, or I will find out which student is responsible for this documentation, or which employee at Julia Hub or the whole set of organizations. So everything should be documented with doc strings, and if you don't find anything within the docs, just get in touch with us, right? We have these Slack channels and such for the feedback. But the purpose here is that the way that substitute works is you give it a symbolic expression and you give it a bunch of rules. These rules are represented in a dictionary. So what I'm going to say is I'm going to take this expression, right? I'm going to say, well, turn the derivative of z by x, so dz dx, just turn that into the number 2, right? And then it'll evaluate this expression that turns, this dz dx into the number 2. And in fact, you can start going all the way, where you can say, okay, now turn, x equals to 3 and, z equal to 1. And you can fully calculate out that if you were to evaluate it there, you get number 10, right? But this is actually the same substitution, right? You can substitute any kind of numbers you want in there. Those could be actual numbers, Julia numbers, or they could be other expressions, right? So you can say substitute, x equals 3z, and now you get a new expression, right? And so you can use this to be able to just keep on building expressions of expressions and substitute other expressions. It's a whole system for transforming expressions into expressions, right? And then as one trick, which I'm just going to show now, just so that way we can use it later, there is also this, that was one step too big. You can also use fixed sub, I believe it's called fixed sub, which does a fixed point substitution. It's the fixed point sub, yes. Thank you. It's not yet. And if you do a fixed point sub, then that means it's going to keep on substituting the rules back. So it's going to say, okay, d of x, dc dx is equal to 2x times c. I'm going to plug that in, then I know plug in x equals 3c, then plug in t 1. And I'm going to recursively keep on plugging this in until I end up with a fixed point, right? And so all these equation manipulations are in there. And these end up being very useful for working with ModelingToolkit. So, again, ModelingToolkit is not a tool in isolation. It's built on top of the symbolic library. And the more you learn about the symbolic library, the more expressive working with ModelingToolkit will be. Right? So for example, I'm just going to copy this one over. So you can also write it down, complicated expressions. And if you're used to something like Mathematica, you'll see that there's also the simplify operation, or what simplify will do is it will give you a simplified representation of whatever you wrote down, right? So you can say, oh, I have x plus x squared plus x squared, and it goes, no, that's actually 2 times x plus x squared, right? It'll perform all these symbolic simplifications for you, so that you don't have to worry about writing everything in the most succinct way. And there's a lot of work that's being done on these simplifiers in many different forms. You'll see that there's other talks talking about things like E-graph simplifiers and things like that. They're simplifying these with other simplification rules, and you can make use of those rules as well. And now the last thing to make note of here is that, as I showed how to do this evaluation, right? You can't always evaluate symbolic expressions by substituting values in. Just that's a form of interpretation. But if you're using Julia, you probably like speed, and speed is not you don't get the fastest thing out of an interpretation, right? So what do you actually want to do is you want the highest performance out of your symbolic variables. Well, what you want to do is you want to generate a code, and you want to JIT compile that code, right? And so one of the core features of symbolics.jl is this function generation process, right? So here, let's say I have this expression. So my expression is equal to sine of x squared plus y squared divided by cosine of z. So let's say I have this symbolic expression, right? What you can do is you can say build function on my expression, and then what you give it as your argument is you give it your argument representation of the function that you want to have. So what do I mean by this? Well, let me show you this by example. So I do x comma y comma z, right? Let me do this based on remove line nums. Now the only thing that this based on remove line nums is it's just removing the line number nodes from here. If you've ever done metaprogramming, you'll know what the line number nodes are. If you don't, I'm just using this as a way to make the printing look nicer. Based on remove line nums thing there. So here's my Julia expression, right? So you can see that it actually spits out an expression in Julia that is just computation. Now, by default, it actually does some nice things, right? It doesn't actually use the default Julia sign function. It uses nanmath.sign, where if you evaluate out of boundaries, it's actually going to use nan instead of errors. Little details like that are useful for numerical solvers, right? So you can see that it's already doing something kind of complex in there. But what did I mean about this, this function representation, right? Well, what I mean by this is that, so here I give it where I say, here's my expression, and I have one thing which is x comma y, and another thing that is z. And what it does is it builds a function where argument 1 is an array of 2 things. And the second argument is a scalar value. And you can see that, that anywhere in my original expression where I had x, it says, you are what R21, here's where y was, and here's where c was, right? So it gives you, so if I say like, oh, I want a function that takes in one vector of 2 things and one scalar value, and build me the function that then does this with x, y, z replaced. It builds you that function. Let's say we just wanted a function that takes in the array x, comma, y, comma, z. Well, you just change your variable list, or you just say, okay, I have x, comma, y, comma, z, and it will then give you the function where it's, okay, now here's a function that takes in one argument, and x, the first argument is x, the second argument is y, third argument is c, and it'll build you the function for that representation, right? And again, this is just giving you the Julia code. So you can take this, JIT compile it with runtime generative functions, or you can just call eval on it. And there you go. Now you have a fast JIT compiled function of your generated code. Yes.
Can you generalize X, Y, and Z to vectors?
Yeah, you can generalize X, Y, and Z to be vectors. In fact, the generalizations in the system are quite insane. So you can also say that these are vector of vectors, and you can even do sparse matrices, right? So you can say, the second argument is a sparse matrix with this sparsity pattern, and it will then specialize the function that's generated based off the sparsity pattern of that of that matrix and such. So yeah, it works off of any Julia abstract array representation in a complex way for the abstract arrays. I won't go into all the details, but it is used, for example, in ModelingToolkit when it is generating utility E, right? It is just a build function of u, comma, p, comma, t, and then gets the code and it compiles it, right? But if you want to build your own functions, say you want to evaluate your Lagrangian from your system, right? You have the symbolic representation, you have the symbolic tools. You can ask it for this function. You can generate this function yourself, right? The world is your oyster to do anything with. So that's symbolics.jl in a nutshell. Again, symbolics.jl has a lot more to it. There's the Grosvenor basis calculation, symbolic integrals, and all this other stuff going on. But this is a subset of symbolics.jl, which is highly relevant to ModelingToolkit. Yeah.
It's about model networks.
Yeah. So neural networks are represented in Symbolics. It is a very recent addition. You can actually see here that if you go to the Symbolic library, you'll see that there's a extension for Lux. This was added, I think, like 3 months ago or so, or 5 months ago. Okay, actually, it's very old now. And you can see that that has actually registered statements applied. So neural network applications on the input vectors will actually carry as a symbolic array function. Again, I'm skipping over a lot of details in symbolics.jl. So, what is at register array symbolic? Well, it's just giving you a new node that is finding neural network evaluations that your neural network is not traced into, right? So, say for example, when you put a symbolic number into a general function, it'll trace out that entire function. You might allow it to do that with matrix multiplication, right? So you might want to just say represent matrix multiplication itself instead of the operations of matrix representation. And so that's what the registration says, right? Okay, you say register this function, and I will no longer trace into it, right? And so there, as of the last 6 months, there's now this register array symbolic, which is for array expressions, which allows you to do to register things like linear algebra and neural network operations. And so, yeah, and this is all the stuff that's been added so that we can support the EDEs in ModelingToolkit correctly. Yes.
What's the average of symbolic derivatives in the world product and this use or different?
Yeah, so that is a very good question, and let me repeat the question for the recording here. So the question was, why would I ever want to use symbolic derivatives in a world where I have forward one automatic differentiation, reverse one automatic differentiation, right? So it turns out that it turns out that these are kind of one and the same thing. So symbolics.jl, the way that it defines its derivatives is it just reads in the derivative rules from the AD libraries. So anything that you can actually differentiate with respect to forward diff, you can actually do the symbolic differentiation of because it's using the same derivative rules under the hood, right? So that's kind of like so you can always do the same things. But why would you want to do symbolic derivatives? Well, they're at their core, they're doing something a little bit different, right? So automatic differentiation works by doing just Jacobian vector products. It's always doing these Jacobian vector products, right? So it's effectively having to do some numerical evaluation mixed with the symbolic evaluation. So it never actually builds that expression. So the purpose of automatic differentiation is that it never builds that full expression. And the reason is because in some cases, you might have, say, expression group, right? And so you might not be able to represent the full expression in memory. And so there's a lot of nice reasons for doing that as a performance optimization, right? But there are other cases where, for example, you want to be able to get the representation of your full derivative and then say, do a symbolic simplification on it, right? Understand that x squared plus y squared equals 1, simplify out values that are sufficiently small, and build a more concise code for the derivative representation, and then compile that code, right? You can't really do that with automatic differentiation. So one way to think about automatic differentiation is it's one way of actually putting the parentheses in an evaluation, but there are 2 to the nth power of different ways of permutating this computation, and symbolic representations can search that space to be able to find the one that is the most computationally efficient. I mean, because you're searching at exponential space, it won't scale for different reasons, which is why you wouldn't do that on neural networks. But there are other cases where you might want to do it, such as for generating optimal differential equation functions.
Yeah. So see, I generate the like expressions. How well does it play with package images? Can you cache those?
Yeah, so you can. So this actually works with package images. That is a great question. So the question was for the audience here was, you have all these nodes that you're generating, but the key is that you're actually generating them at runtime, right? And you're evaluating them, right? How do you make sure that these are all cached into your Julia package library so that we get rid of the JIT compilation on startup, right? This is actually something that we had just solved in the last 2 months here. So I'm happy to share it. We just put this tutorial up. And I think it might only be on the dev version, or do you know where this tutorial is? Or
Yes, we have a dev for that.
I thought it was just up here. Working with pre-compilation binary building. Okay, cool. Yeah, I mean it's pretty new. So the key is you do have to tell it when you do have to tell it when you evaluate it, like which model to evaluate into. You need to make sure you evaluate it into the right place, so that way it knows how to put in the package image. Well, there's documentation in here that shows you how to do this effectively. And then so you can use symbolic to be able to generate out these functions, and then you cache these functions, you compile these functions, and you cache the compilation. So that way in the future, when you say using my giant model, it just has that binary already built. Yeah. This is something that is rather new. So if the documentation is not complete enough for you, please just let me know. Yeah.
So back to a deep topic. There's also, for example, enzyme, which says, I let LLVM do a lot of the optimization, right? So you say, and if we do a lot of optimization, and you maybe say one sentence about letting LLVM versus your.
Yeah. So it's a very deep topic. But I think that the way to describe it is compilers have a lot more rules to follow. Like, what's a good example? Like how when you walk around in Germany, people stop at the stoplight when it's red and they don't cross the street, right? It's the compiler is like that, where it says, there's a rule here that says, x minus x is not necessarily equal to 0 because it could also be equal to -0, right? So I'm not going to eliminate this computation. Whereas with a symbolic library, you can say, the rules for my simplification include x minus x equals 0, right? And so you can tell it all sorts, or you can say 1 times 10 to the minus 16th times a variable is equal to 0, right? You can tell the simplifier, you can tell these custom substitutions, and you can really generate much more optimized code for these cases where compilers are not, the compilers are not allowed to make these assumptions because there's all sorts of things, right? Like, for example, 0 times a variable is not necessarily a 0 because I think that there's 0 times inf is a nan or something, right? And so it won't actually just zero that out. And so again, so things that are doing compiler optimizations at the LLVM level are a lot less flexible than if you're to do your own custom optimizations, right? And so we actually have some talks around using eGraphs for custom compiler optimizations and such, and this is where that all comes into play. Yeah? Let's go with Owen first.
Yeah. So what I was thinking about when you were showing that unrolled ODE solve was that it seems like a lot of the time you're going to run into sort of exponential blow up of the size of an expression tree. But of course, it's not actually exponential blow up of size used because, if you're using the same allocated expressions, it's like basically a DAG. Is there a way to visualize that DAG?
JuliaCon compiler. This is how JuliaCon compiler does a lot of its optimization. So instead of trying to represent the well, no, I mean, we're also working on some open source things with the eGraph stuff that Alessandro Cello is doing. The eGraphs end up doing a DAG representation instead. And so, yeah, there's some work going on in improving the symbolic representations, and a lot of them are making use of the fact that most of all the symbolic expressions that we built through tracing are actually DAGs instead of full trees. And so you can use it as an optimization within the simplifier. And anyone that's interested in working on new simplification techniques, this is a very strong ongoing community. I think there's like 7 or 8 people involved. We're always looking for more people who want to get involved. And there's some very fun math there. But yes, yeah. So these DAG optimizations are, if you actually look at the issues list for symbolics, there was actually one about optimizations using DAGs that opened a month ago. Another one was all around things like, argument sorting, right? So you don't actually have to sort your arguments all the time. You can decrease computations like that. So there's all sorts of stuff going on in symbolics that are using these kinds of ideas. Yeah. And also,
earlier you cited an interesting example where the symbolics is when it comes to the adjuncts, it'll pull already with that. Are we getting it's an example of the corner waker use it's called right the adjunct that'll be to know the computation.
Yeah. So the question was, okay, let's you want to you use symbolics to be able to you use symbolics to be able to well, it uses all the rules from the AD libraries for its derivatives, but could you actually use that to be able to write better derivatives for the AD libraries? Turns out this is actually useful. So actually people do this all the time. So a lot of the rules that people use with chain rules and stuff, a lot of them have been checked by using symbolics. And actually for the creation of AD libraries as well, for example, if you go back to some early tweaks in Diffractor, you'll see that Kenna was actually using symbolics and in symbolic variables to be able to test whether Diffractor was giving you out the right expressions, right? And so there's a very nice connection between them. And then let me show you this, right? So let's say we had this expression. I might still have A defined in here. Or I have some symbolic array, right? So let's say I have a symbolic array. Right. So I say, I have this expression that is like A is equal to this, right? And then I have my vector is equal to, X, Y maybe, right? So whenever you create one of these adjoint rules, right, what you're actually calculating is A prime times V, right? And, the Jacobian vector the Jacobian transpose multiplied by a vector. So what you can do is you can actually just say simplify the A times V calculation and then do a direct code generation based off of that and use that actually as hard code, write that as your adjoint rule for your function. And this is actually one way this is one way to very easily derive function. And if you're then trying to find out like, oh, what is the general rule for the adjoint of a Cholesky factorization? One really nice way to come up with it is you work with what is the 2x2 case, what is the 3x3 case. You let symbolics generate this. You see what the pattern is. You write the pattern down and you prove it by induction, and now you have your AD rule, right? And so this is why it's very easy. We actually do use this all the time for coming up with our AD rule. So yeah, that's a very great question. Can you use the symbolics as a way to be able to help you with automatic differentiation? Yeah, the two are not actually so different. This is why we both work on symbolic differentiation and the automatic differentiation tools. They connect to each other very well. Yep.
When you have to generate your
Yeah. So you asked about static compilation, right? So you can generate this Julia code and you can statically compile this to a binary. That's what I showed in the documentation over there, right? There's also ways to be able to generate C code and stuff from this, right? So there's a C code target, and then also JuliaCon compiler has a direct to LLVM target that is retargetable to other devices as well. So yeah, there's forms of static compilation possible on these expressions. Yep.
Then APN.
I just showed you how to do the JVP live, right? So, you just take your Jacobian, you multiply it by your vector, and then you get the Jacobian vector expression, right? So there doesn't, yeah. So you just build the expression for the Jacobian times vector, then you can do any function generation based off of it. Yeah. So the question was, are there, so AD libraries, they always work by JVPs and DJPs, like Jacobian vector products. Is there a way of doing that in symbolics, right? The way that you do it is you just calculate your Jacobian, and you just say transpose it, multiply it by your vector, and then you get the symbolic representation for the JVP. You can do code generation based off of that. So it's a different way of looking at it, but again, it's actually a bit more expressive. And it turns out that there are certain things that you can do with the symbolic derivatives of sparse matrices that automatic differentiation is not able to do in terms of its optimizations. There's cases where automatic differentiation has to do O of n calculations, whereas symbolic differentiation only has to do O of 1 on certain sparse matrices, and all sorts of different cases. So I'd be happy to talk with anyone in more detail about the differences between the two. But yeah, symbolic differentiation has its use cases, and automatic differentiation has its use cases. And I think that the use cases that use both of them are some of the most interesting. So anyone else have any questions here? It seems like we got a lot of folks that are really interested in. All right, more questions. Yeah.
What comments of modeling without the next
So performance is on Modeling Toolkit without JuliaCon compiler. It does really well for models that have about 500 or to 1,000 equations or less. It tends to do less well as you get to the larger set of equations. That requires this alternative compiler that does a direct LLVM backend. There are certain issues that are being worked on in Julia for improving that scaling, but it's more for that kind of range of models, right? And again, it's really just because purely symbolic representations have limitations as your expressions get rather large. And so having a separate representation that is based off intermediate representation that is more like programming language, that is useful for the larger equations. But there is a trade-off, because when you then move to this other form, you can't actually do things like substitution or all these other tools with it. So there's a nice trade-off. It turns out then that Modeling Toolkit in the symbolic code generation, it has this limitation of size about 500 to 1,000, but it is a lot more interactive and usable for kind of debugging and such. And then you can switch to the other one as a performance optimization. But yeah, then there's all sorts of other compilation tools being built. I think that Mason Prodder, I don't know if I actually see him in the room here, he's building a thing where if you have purely causal models, he's building a thing that way purely symbolic representations never have to do equation expansion. And then he's able to do graph systems that are like thousands or millions of nodes on causal systems that have a causal graph line. So that's part of the NeuralBrox project. So there's a lot, and then there's like some of the people doing things like power systems and dynamics, that's some other compilation tools. So there's a whole ecosystem of other compiler tools, and they all kind of play together. And within the SciML benchmarks, we're really starting to try to start benchmarking a lot more of this. You'll see that there's now a Modeling Toolkit section in there that's starting to benchmark a lot of these compiler tools. So yeah, there's a lot to talk about there, and I'd be happy to talk about in more detail. But yeah, there are limitations to the purely symbolic form, but there's also benefits you get from it. So using the symbolic stuff in the right context is really the core of doing symbolics correctly. I think that there was one other question. Sebastian? Yeah. So I'm going to only very quickly just mention that. So for symbolic variables, symbolic variables can also have types. So you could tell it, I don't want complex numbers or certain things like that. And then what that will do is it'll actually change the simplification rules, right? So if you say it's quaternion, then it actually has. I don't know if we ever emerged in this, but for example, the simplification rules are dependent on the type. So it actually checks the type. By default, the type is real. And so, for example, if you have a type, by default, the type is real. And so for real, you end up having simplification rules like x minus x is equal to 0, right? But first, if you then say like, the type of this is float 64, floating point numbers don't have the property that x minus x is equal to 0, so it won't actually simplify it out. So the simplification rules are type dependent, and then complex numbers have their type dependent stuff. And I don't know if we have all the derivative rules on complex numbers yet, but again, that'd be a perfect thing if anyone is interested in helping build out the symbolic library. It's a great place to contribute if you just know a little bit of math. It's not so hard to really dive into. Any other questions? Yep.
Optimize intelligent vision of the English compared to the system.
Yeah. So JuliaCon compiler can generate direct to LLVM and direct to C code. We use this for things that require specific types of C code for embedded devices, right? And in fact, there'll be part of the keynote tomorrow that we'll have Gary from Boeing. We'll be talking. I think that we might touch a little bit on that. Yeah. Okay. One more question. Yeah.
Is it also possible to have constraints that picks this real and positive?
Yeah. So the question was, is it possible to have constraints like x is real and x is positive? Yeah. So well, first of all, I mean the type of this defaults to being real, right? So that helps through that part. But the fact that x has to be positive, you can write these constraints. So you can write symbolically that x is greater than 0, right? And so things like if you define a symbolic optimization system The way that you define your constraint equations are symbolically as well. It'll know how to code gen, for example, to IP opt and be able to say, hey, I have this inequality constraint and now specialize on this. So the optimizers are able to handle this. You cannot do this with optimization with differential equations right now. Though a lot of the work in the MIT Julia lab is to be able to build new solvers that can do differential inequalities or differential inclusions. We don't have the solvers for that right now, but you go see the SciML roadmap in the state of SciML talk, right? It may mention differential inclusions as one of the things we're building towards. Be able to mix differential algebraic equations with inequalities. But for right now, you can't mix the two. If you do mix the two, it'll just tell you it doesn't know how to code gen for that. All right, cool. So that's symbolics, which, again, in its own right, symbolics is a very interesting piece. But now the next piece is, how do we actually use symbolics with Modeling Toolkit to be able to build models in this, interactive symbolic form? And if anyone can give me some water, that'd be great. But okay, that's only a quick side note. So now let's go to Modeling Toolkit. Right? So Modeling Toolkit is now this library where we use these symbolic expressions, right? So now the first thing that I'm going to show here is that I'm going to pull in T units, T units, T. Right, so I'm going to pull in these standard definitions of what T and the derivative with respect to T are from the library, because the reason why we do this is that we want one definition of time. We want one definition of derivatives that's used to go across all of our different symbolic representations, right? And there's reason for this as well, because, you can write your differential equation, so you can say like tau is equal to 10 times T, right? And then you can write, your new differential operator. You can write differential equations in terms of tau, and then say, hey, do this time change from tau to T for me. So there's all sorts of different time things that you can do symbolically. But keep things simple. We're just going to say, and most of the tutorials say, let's try the standard time. So you have the standard derivative, right? And so now let's write down the Lock-Voltaire equations, right? Because this is not a SciML talk without the Lock-Voltaire equations involved, right? So, if you've seen any of our other tutorials, this just got to be there, right? So we do at variables, and you got to do the classic, rabbit, you got to do the classic wolf. But now I have to say that these are actually variables that are dependent on time, right? Now, why do you be able to say that these variables are dependent on time? Well, because otherwise the derivative with respect to the variable, or the derivative of the variable with respect to time is 0, right? So again, we want to make sure that all of our relationships are well defined, because the symbolic simplifier wants to be well defined in its operations, right? So now we then do our parameters, right? And if you didn't know what I was doing there, I'm just going to do backslash and then Julia. If you have the Julia VS Code extension involved, it has this autocompletes for Unicode. Unicode also includes emojis inside of the specification. Who knows why they spent more time on doing that rather than getting things like underscore P, or no, underscore Q is actually not in Unicode, but the emoji wolf is. I don't know why. If you take that up with the Unicode committee, that's actually something like literally in the Unicode spec. It has it has this wolf symbol, but it does not have underscore Q. But this, we'll leave that part aside. So okay, we don't use some underscores and such, but we can use any Unicode we want. And now let's write down our equations, right? So okay, so our equations are going to be, d of rabbit, right? So again, this is the differential operator. So d rabbit dt. This is equal to alpha times rabbit. Now I'm just going to write down the Lock-Voltaire equations here. Beta times rabbit times wolf. And then our other equation is d wolf dt is equal to minus gamma times wolf. And thank you. You're amazing, and your mother probably loves you. Cool. Delta times rabbit times wolf. And I'm also going to add an extra equation here. So I'm going to just say the total population is equal to the number of rabbits plus the number of wolves, right? And you can say, oh, but that's not an ODE, right? There's no derivative for the total equation. Well, implicitly, if you actually take the derivative of this expression, right, the derivative of health is equal to the derivative of rabbit plus the derivative of wolf, and you can substitute in, et cetera, et cetera. So you can actually write this as an ODE. But it turns out that this is a differential algebraic equation, right? So there are two differential equations here, and there's one algebraic expression. And so this is a system of three variables that we can solve for in time, right? So there you go. This is our Rackauckas equations. And again, if you haven't written down the Rackauckas equation, you can just copy it from the flitter. Okay. So if you're following along, you now have this thing of three equations. And the first question that you might ask is, whoa. We say d rabbit dt equals, rabbit of t, but you're putting this tilde sign in there. Like, why would you use tilde, right? And, yeah, so Wikipedia thinks it knows why I use tilde, but this is AI is wrong, right? Okay. So why do we use tilde here? Well, so the reason is because equals in a computer programming language, it's been co-opted for nefarious purposes, right? So equals in a programming language means, so I say A equals 2, and I say A equals 3, and it is perfectly fine saying that both of these are true, right? Because equals is not actually what equals means in a programming language. Equals means the, I'm forgetting the word right now. Yeah, equals means assignment in an imperative programming language. So equals has been co-opted, and this is not just Julia, right? Most programming languages have equals mean assignment. There are some programming languages that don't do that, but we're not going to talk about that. But what that means is that equals is assignment, and it's not really the symbolic equality. You can't guarantee that something that is equals is always going to be equals, right? So what we did is we just said, okay, what's the closest thing to equals that is easy to type? It's tilde. And so whenever we want to write a symbolic equation, we should say this tilde expression means equality between the two sides, right? So that is one little thing to make note of. It's a little quirk that you might see, but you get used to it rather fast. Okay, and now what do? Well, we say, okay, this is our ODE system that we want to handle. So we do add modeling toolkit build, MTK build, the system with ODE system equations, T, right? So what does this macro do? Yeah, so you'll see that in the SciML, when the docs interfaces and everything talk on SciML, one of our properties is that every single time you have a macro, it should be obvious what that syntactic sugar stands for, right? So what does add MTK build actually do? I'll be showing all the different steps here in a second, but what is this doing is saying ODE system of equations, T, name equals system, and then what it's going to do is then going to do complete, or it's going to then call structural simplify, and then it's going to call complete on it, right? And yes, this is the perfect time to ask that question because so first of all, what's going on here? Well, the reason why it has this name property is because, let's say you're writing a file reader, right? So in Julia, I'm calling this thing sys, right? This is the name of the variable, right? But if you're writing something that's, say, looping over files and building ODE systems, you might not actually want to, the variable name that you have in your code might not necessarily be the variable name, the name that you want of your ODE system, right? That might be a name given to you, say, in a file, right? And so the two might necessarily want to be different, but in most cases, if you're working interactively in the REPL, you want to make sure the two are named the same. So that would generate a law tech of say, oh, this thing is your system they're talking about. It uses the right name, right? And so you'll see that there are ways to be able to just, so when I did say, variable X, right? It builds a new variable that is named X, but also has the symbol that knows it's X, right? You can actually disconnect the two, so that way you can read in these variables from a file, and they can have a name that is named from the file. So these macros are really just helpful for this interactive use, but there are always ways to be able to disconnect the Julia naming from the naming of the variables itself, right? So this is one step of that MTK build, right? The next step is structural simplification, and the next step is calling this complete on it, which I want to then talk about here, because the moment we can do this at MTK build, it tells us that we have a system that has two equations, right? Which should look rather weird because it just, we haven't been here for so long, and it was just right up here that I gave you 3 equations, and now you're telling me you have 2, right? Well, again, what's going on here is that it uses a structural simplification process, right? And what it's doing is it says, oh, actually, I know how to be able to build, if I know how to calculate rabbit and non-epic walls, then from these 2 things, I can actually calculate totals. So I actually don't need to solve for that, right? And so the structural simplification will delete equations that it feels it doesn't need to solve for. And if you ever want the solution, I'll show you how to get that in a second. But right, this is why the structural simplification is here. And then the next part of the talk will go into a lot more detail on what it's doing. And the last thing complete, that we'll get into that with the Acausal modeling part. But okay, so as you can see that there's something interesting going on already with the simplification. But let's actually just solve our first problem here. So what we did then is we use systems just like they were our ODE function. So we just say, my problem is, ODE problem, where instead of giving it an ODE, I give it my ODE system, right? My simplified ODE system with two equations, and now I have to give it my initial conditions. So I say, the starting rabbit is equal to 1.0, and starting wolf, not woman's shoe, wolf is 1.0, and then I give it a time span, right? Oh, and then it gives me an error, and it gives me this error that says some parameters have, please provide a default for the following variables. Oh, but I forgot to define my parameter values. So I also need to do the same here. Alpha is equal to 1.5, beta is equal to 1.0, gamma is equal to 3.0, and delta is equal to 1.0, right? So it tells you like, oh, hey, you need to provide these values. And so the key thing here, right, the difference between ModelingToolkit and symbolic is that everything here we're writing down symbolically, right? I'm not giving it an array of numbers. I'm giving it an array of symbolic maps. So why is this important? Well, it's important because, again, remember, it's changed our equations, right? So I might have given it like, okay, I have, rabbits, wolves, and toad, but it simplified it down to just two things. And so we'll see in the initialization section this becomes important, but really what you want to do is you just want to say, here's my initial conditions for the things I know, and try to build a system if you can, right? Because it might have simplified up something else, but it could still solve for it itself. So I could actually do this differently, right? So I could say the number of rabbits is 1, and the total number of things is 2. And it will then also be able to say, okay, you know what? I'm actually not solving for the total number of things, but I'll be able to calculate out what the initial condition for wolves will be on demand when I need it, right? And so what this means is that you want to interact with this symbolically, because you don't actually then need to know, all what it's actually doing under the hood, what equations it's solving for can be abstracted away, because that allows it to be able to do any symbolic simplifications it wants, right? So you just have to be able to say, here's what I want to be true. I want the initial condition of total to be 2, and I want the initial condition of rabbit to be 1, and it's going to give you an ODE that doesn't have a 2 in the initial conditions at all, because it should be, it gives you the 0 because that's just the guess. Well, I can actually show you that when it does the solve, it'll do an initialization process and give you the correct initial value. So let me actually show you this right now then. All right, solve this. And you can see here that, even if it gives you this problem where it starts it out with, rabbits equals to 1, wolves equals to 1, and then it solves it, right? And so you're able to just interact with the symbolic. You don't actually have to know variable uses in the end. You just say, these are the things I know. This symbolic thing is like this, symbolic thing is like this. That also means that this is how we handle the output as well, right? The output is an array of 2 things, but we have 3 equations, right? So how do we make this mapping, right? So this is where the symbolic indexing interface comes into play, right? So if you then just say, give me the solution, the time series solution of rabbit, right? You're able to work with all the tools in ModelingToolkit using the symbolic representations that you use for the ModelingToolkit model. So you just say index it by the value rabbit, and it gives you the time series for the solution of rabbit, right? And now remember that it had these 2 equations, and it completely removed the total equation from it. But if we then ask for, say, give me the solution for the total, it will then give you the solution, those values created on demand, right? And now it's actually smart enough. So here's another party trick. If I say toad squared plus, the sign of rabbit, right? It will actually just generate on demand the expression and give you the time series for those outputs. For any variables that you want.
So I see that you on your parameters, initial value, you specify no 64. So
Yep.
what happens if you use integers?
Yeah. So that's a very good question. So you said, oh, I see that inside of your initial values that you used floating point numbers. What happens if you use integers? Well, the ODE solver will actually correct that for you, because if you try to use an initial condition of of integers in an ODE, it knows that you can't solve an ODE on integers. That won't be well defined, so it fixes that for you. But if you use parameters, your parameters will actually have an interesting property that, yes, some parameters can be integer valued, others can be other parameters can be floating point valued, and so if you actually try to look into it, you'll see that there's this modeling toolkit parameter struct. It's actually a tuple of vectors that was able to be type stable, keeping different things. And that means that you can have one parameter be an array, you can have one parameter be one parameter that is an array of integers, another parameter that is an array of floating point values, and another parameter that is a ODE an interpolation object, right? And all these parameters can be used inside of the code in a way that is type stable and actually generates fast differentiation code. So you can mix all sorts of types as your parameters. So something to then mention. But next thing to note though is, okay, so in the thing here, I didn't actually put the parameter values here. So what's the difference? Why are my notes different from what I did? Right? And I was trying to see if anyone would ask that question, but you guys all failed the quiz. You all get a F, and so the difference here is that you'll notice that inside of this version of the function, it said that there are these default values, right? And so that's because when I define the parameters over on this side, I actually put that the parameter is equal to given value, right? So instead of just doing parameters alpha, beta, delta, it actually just said, this parameter equals, this parameter equals, this parameter equals. And if you do these default values, what it ends up doing, right? So if I do, these default values, equals 3.0 and equals 1.0, right? If I do these default values, then now I no longer need to actually specify these things here, because it knows how to, I need to recreate the system, but now it knows how to grab the defaults, right? But now when we mean by defaults is that the defaults are what happens if you don't specify anything else. And so this is a nice feature, being to be able to create a standard form of your model, but then you can just say, well, let me see what happens if I change, alpha equal to, 2.0, right? And you can just create it with alpha equals 2.0 and solve it, right? You can just change one parameter at a time, all symbolically, right?
Just one thing, maybe we could have a break. There's copy right now. In case people want to have a break.
Oh, I mean, why would anyone want to break from this?
Because if it
I mean, yeah, if you want to take a break, we can. You got a question?
Can you make
be patient with this old stage emphasis?
Yeah, so
You won't have the string sign off set.
okay, yeah, so you can use the event handling for that. So again, I won't go into that during this, but I'd be happy to show you this in the documentation and such afterwards. But yeah, so the question was, can you mix constraints? So you can come up with events that tell you, like if x crosses equal to 0, or if x goes negative, then do something else and such. So you can have, again, everything that you can do with the differential equation solver itself, all the event handling and such. There are ways to be able to do this with the modeling toolkit and the symbolic tools as well. Yep.
Related to this question, let's say that in this case, knowledge instead of being a variable would be a 0. Could you enforce that with this?
So instead of being a variable, it could be
Just a 0 or something, so that I'm enforcing that break. 0 would be difficult. Right? What? Yeah, because you have negative rabbits.
Yeah. Okay. Oh, so yeah. I mean, yeah. So I'll show in a case with a constraint equation in a second. The Cartesian pendulum is a great case of that. So that'll show up in a little bit. All right. Cool. I think that is. So that's the basics on the modeling toolkit. Yeah, and so then, for example, so instead of just doing ODE systems, you can also say my problem is like a steady state problem, right? So you can also do steady state problems and all the other things inside of the SciML libraries, right? Again, this is just a symbolic representation. Here, maybe this means well. Yes. Okay. So, all the things that you have inside of the SciML libraries, like you have, ODE solvers, you have optimization libraries, you have the SD solvers and such, right? You can create these systems and then generate code to those systems just by having the symbolic representation. And then you call the numerical problem code on the system, and it generates the numerical problem for that, right? So that's the basics of Modeling Toolkit. And now we're kind of at the end of that first first notebook, right? So the next thing, well, after a bunch of questions, then we'll go into Acausal modeling. Yeah.
What can you see also a little bit interesting?
I think that I just need to that needs improvement in the initializer, right? So the initializer. Okay, I'll just speak louder then until this gets back. Okay, cool. So it's for the initializer. I think that I just saw right now live that the initializer wasn't set up on steady state problem as it is for OV problem, and I'll show you the initialization system that's handling all that input. So the initialization system is new as of a few months ago, and it just needs to be added to that as well. So yeah, that was just a bug that I ran into live, and that's why you don't just live code everything. Yeah. Is it possible to have parameters that depend on time? Yes, you can have time-dependent expressions. You can also have parameter expressions that are dependent on other parameter expressions. So that way, if you change one of these parameters, it changes your other parameters as well. So you can go to the documentation about dependent parameters and all these kinds of details. And then you can also have a parameter that is a function itself. So for example, you can have an interpolation object that is like an interpolation over data and time. And you can have that be a parameter, and then you can use that parameter to call it by time, as inside of your function. That's actually how the sample data components inside of ModelingToolkit are implemented, right? So all these things, you could, again, all you'd have to do is that your parameter would just be, your parameter would then just have to be, a gamma of t, and then it would know how to throw gen for that. Yeah.
So in very concrete, it wasn't all just not input stuff. Was I don't know this exact unequal form where like alphas and things. Can I do easy sensitivity analysis without having to repeatedly solve this equation or this?
Yeah. So the question is, can you do some special sensitivity analysis things? You can make use of all of the numerical sensitivity analysis tools. It turns out for a lot of ODEs, unless there's an analytical solution to the expression, you do actually have to do the sensitivity analysis on the differential equation solver. So all the stuff with SciML sensitivity and those local sensitivity analysis, you have to make use of those tools for that. There are cases where it can actually find an analytical solution for you, in which case it can derive the analytical solution on the sensitivity analysis too. But that's rather rare because most ODEs don't have an analytical solution. And that is actually a funny case that can happen here. So if you have an ODE that has an analytical solution, it'll generate a numerical problem where the initial condition is nothing. And then if you put it into the ODE solver, it will still solve it. And you symbolically ask it for the answer, it'll still give you the answer. It's just not calling the ODE solver at all. It's just using the same workflow. So that way it works, your code always works, but it might actually solve nothing. It might actually do the entire analytical solution symbolically.
Just an extra announcement. There's an extra room that's mirroring this one for people that would like to go there and have better seats. Just for so for you to be more comfortable. We will not have Chris, but we have better seats. Just letting you know.
All right, we'll see if people care about me or seats.
For you.
But yeah, so just to mention, if it wasn't loud enough, there are other seats in another spillover room, because again, this is standing room only. Thank you everyone for the excitement, but but that also means that it has its own logistical issues, right? So so now let's go on to this next part. Where did all of my? So the next thing, which is we haven't even gotten into anything that is hierarchical modeling yet. So now this is actually the hierarchical part, which is the Acausal modeling with right? So again, so the purpose of symbolic modeling, right? So you've already seen that there's many other purposes for having a symbolic modeling tool, right? Being able to differentiate and generate expressions. And other people are asking questions online like, oh, what if I want to represent my ODE as a Lagrangian and automatically generate the ODE system? Well, it should be very clear how to implement that now, right? Like you can do that as a hackathon project in about an hour, right? So all these things, there's many reasons for symbolic modeling. But one of the core things that ModelingToolkit has is Acausal modeling as part of it. So what does that mean, and why is that useful to you, right? And so let's start again by, I already have this all live in my session, but I'm just going to pull this all in here. I say using modeling toolkit plots, ordinary diffq, right? Going to pull this all in. And now I'm going to say, okay, so what are we going to, how do we actually build an Acausal model? So, I mentioned very briefly what it is. Now, the second time around, which again, it might still not make sense the second time around, but let's go through the flow. Let's actually build the RC circuit using the components from the Modeling Toolkit standard library, right? So the Modeling Toolkit standard library is this library where if you go to it, Modeling Toolkit standard library, you'll go to this library and you'll see that there's this library of all these different components, right? It says like, oh, there's a component that is a capacitor. Oh, great! It has a 1 port. What does all of this mean, right? Let's get into this. Like, let's start to understand how can we use these libraries of components, right? So okay, so let's pull this in. So let's say we want to build the RC circuit. So the best thing, the nicest thing to have for the RC circuit is you probably want the electrical library that has all the electrical components. We grabbed our electrical components. I'm also going to grab the Modeling Toolkit standard library blocks library, which has a lot of the basic blocks. And what I want from there is constant, because I want to be able to drive this RC circuit with the constant voltage input, right? So I'm just pulling in, these libraries of components. I'm going to define a few constant values. They're all going to be equal to 1 because that makes my life easier. So I define a few constants, and now let's actually build the model, right? So what I'm going to do is I'm going to say at mtk model, right? So I'm going to build a composed model by using the mtk model, which there is a way to be able to do all of this without using the macros. But if you want, but most of the documentation uses the macros as a simplified form. And now what I'm going to do is I'm going to do the following. I'm going to first start by telling you what components I want, right? So I'm going to say what I want is I'm going to want a resistor. So let me write this down. I'm going to say it, right? I want to build a resistor, and I want to name this object little resistor, right? So this little resistor is an instantiation of the resistor component where the resistance is equal to 1.0, right? And I want to build a capacitor equal to the capacitor with this capacitance C equal to 1.0. Whoops, I need to evaluate it. I want my source term. Well, I'm going to have my source be a constant voltage with V equal to 1.0. I'm going to have my ground term. Well, I'm just going to build a ground, and ground doesn't have a value given. Oops. I instinctively always just hit a shift enter. And now I'm going to do is I'm going to add equations begin, right? So when you build a model, you can also tag more equations to it. So what equations do I want to tag to this? Well, what I want to do is I want to tag all my connection equations, right? So what I want to do here is right? So I want to have this kind of circuit where I have this with constant voltage, with the constant voltage, and I want to connect this resistor, and I want to have this resistor here. I want to have this capacitor, and I want to connect this here. Then this goes to ground, right? So what I want to do here is I want to say this pin on the constant voltage goes to this pin on the resistor. This pin on the resistor goes to this pin on the capacitor. Right? So I'm just going to say, what I'm going to do is I'm going to say, here's how all my electrical components connect, right? And so the way that you read this is that you just say, I want to connect the source, the positive pin of my source to the positive pin of the resistor. I want to connect the negative pin of the resistor, so resistor.n, the negative pin, to the positive pin of the capacitor.p. I want to connect the negative pin of the capacitor to the positive pin of the source, right? So that completes the circle. But I also want to connect right there. I want to connect the capacitor dot, and I want to also connect this to ground, right? And that should be my full set of equations, right? And again, this is just an instantiation of this graph, right? This is the positive, this is a positive pin, this is a positive pin, negative pin, and then a negative pin, right? So just all I said here to be able to build this set of equations is here are the components. I have constant voltage, I have a resistor, I have a capacitor, I have a ground, and here's how all these pins are connected. And so I basically just made that diagram. And now that itself is a model, right? And what I can do then is I can say at mtk build, this RC model. So I build this model equal to an instantiation of the RC model. And what I get is, did I misspell something?
Brought a constant blocks on the church. You need to connect.
Oops, what I just... Good. Wait, how is that? How is this working yesterday then? Let me look at my notes here. Well, my notes are just the tutorials of the library. Oh, it should just be constant, yeah.
Although constant comes from blocks, that one. You have to have source. You have to source any constant.
Oh yeah. I don't know how my note was notes were working there. Maybe I just did out of order execution or something. And then source is equal to a voltage. And then the constant K equals to V.
And then you still need to connect to tell me you're not.
Yeah, I do need to connect the capacitor to the source that,
you can see the gradient on first.
Yeah, what was the piece of? Oh, yes. Oh, yeah. Yeah, so I need to connect the constant dot output so that way the source version actually has a constant defined on it. Perfect. All right. So basically, in this constant voltage, right, it's really just there's a constant, right? So there's a constant that is then connected to this that is connected to this constant voltage thing that it's in not active. So why is that there? Well, that's a units thing, right? Because the constant is just a number, but it needs to be able to know how to connect to electrical components, right? So you have to transform from being just a constant number to being a constant thing that is a voltage, right? So that's what this unit conversion is here, right? So I have a voltage source which has a value that is given by the constant that's connected to it. So, all right, cool. So I build all of that, and then it tells me that I have one equation. So what is this equation in here? So equations of RC underscore model. This is D capacitor, so voltage of the capacitor dt is equal to I divided by capacitor. Great, we got the capacitance equation, right? And if you solve this, it should follow what you did with elementary physics, right? So you just say, so you then just say, let's say, I'm writing my notes now. U0 is equal to, sys dot, I really messed up those notes. Okay, I'll have to update those notes. So RC model dot capacitor dot V is equal to 0.0. So I start the capacitor voltage at 0, and then I say, prob equals ODE problem of my system, U0, 0.0, 10.0, and
that is just.
Oops. Good point. Right, and so I built the problem, right? And then I just solved the problem. And now if you got a little bit lost here, that's perfectly okay. We're going to go back through it in a different way. I'm just showing you that now we have solved the RC circuit by just piecing it all together. Right? You can see here that we get this plot where it says, this is the voltage of the capacitor. It starts at our initial condition that we gave for it, 0, and then it just solves until it hits its 1, which is basically just, we're setting that's voltage 0, and then it fills up with capacitance. The reason why it ends up at 1 is because the resistance is equal to 1, the capacitance is equal to 1. Yeah, exactly. So let's go back to this. Okay, so let's go back through this a little bit. So the model is So I have a resistor, right? It's just this diagram, right? So I have a resistor, I have a capacitor, I have a ground, I have a voltage, and I have a constant. What I do is I connect my constant to my voltage, the voltage source, and to be able to define what the constant voltage value is. And I connect the voltage source to the plus pin on the resistor, the negative pin on the resistor, the positive pin on the capacitor, the negative pin on the capacitor to both the ground and the negative pin on the source, right? So that's this graph here, right? And now
This is worth adding that the constant voltage value is 1, whereas the initial capacitor voltage is 0.
Yeah. And so this gives me an equation, right? So it gives me a system of equations, which it simplifies down to one equation. We'll talk about how it gets there in a second. But then I give it this initial condition, right? I then just say, I want to run this where the initial voltage here is equal to 0. And okay, I got it. It started with the initial voltage equal to 0. We solve it, and then we get this nice curve, right? But what is actually going on under the hood, and why do we get this one equation, right? So what actually happened under the surface? So remember, at MTK build has the simplification step in there. Let's actually start to strip away the simplification and understand the different steps, right? So if I do this, instead of doing at MTK build, if I just instead do at named, it won't run the simplification. It won't run the completion step. It will actually show me what all these equations are. And this is what I've generated on the wall. And so what do you actually see inside of here? I mean, you see that you have your different connection equations, right? Which says connected here, connected here, connected here. And we have all these other equations, which are these are the equations that come embedded inside of these components. And what ModelingToolkit will do is it'll take all of that and it'll simplify it down. So what do I mean by that? Let's go back to slideshow mode for a little bit. So again, if you're not understanding fully what a Acausal model is doing right now, that's okay. That was step one, just showing you, let's build a model, let's solve it. This is how we do connections. But now, what do connections actually mean, right? That's a really big deal here. So first of all, what is the difference between Acausal modeling and Acausal modeling? And so Acausal modeling is useful and something that has kind of been gaining steam in a lot of industrial contexts because you get a lot more equation reuse out of it, which is how I'll show you in a second, right? And the theme that is different between causal modeling and acausal modeling is that notice that all the connections I have here, right? I did not say this is the output and this is the input, right? There is no such thing as input output. I just connect things, and connections create these weird equality relationships. So the difference between causal models and acausal models is that with acausal models, we specify what is equal, what is true. We specify instead of connections, we don't need to specify what are inputs and what are outputs. What this means is that you can have your system, and we'll show you in a second, but it allows you to get a lot more code reuse out of your physical components. But to really understand what the difference is, I want to do a show not tell example. Yeah.
Possible to have a component that has several inputs and several outputs.
Yeah, you can have a component that has several inputs and outputs. So since acausal modeling is a superset of causal modeling, you can actually see that you can define inputs and outputs on components. And in fact, the constant voltage is something that has an input-output behavior.
But I think maybe more general questions, can a component have multiple interactions, not just two, right? Causal and acausal interactions.
Yeah, you can mix causal interactions and acausal interactions. You can have acausal connectors, and you can have inputs, and you can have outputs. You got multiple of each of those as well.
So, an example of your planetary gear is an example of a map of the button. It doesn't have 2 ports, it has 3 ports. And so you can handle those as well. They don't just have to have 2 interaction points.
So causal versus acausal modeling, show, don't tell. I mean, just out of curiosity, how many people are familiar with causal modeling and have used simulink in some capacity before? Yeah, so it's a smaller group of people, I mean, especially with this kind of crowd. But so I'm going to actually go into what the causal modeling process looks like before showing you the causal solution, right? So here's what the RC circuit looks like in a causal sense, right? So first of all, you have here's the system that I want to have around my RC circuit. And I have Kirchhoff's voltage law, right? So the voltage of the resistor plus the voltage of the capacitor is equal to the constant voltage, right? And when you go around a loop, it should all sum to 0, right? And you have Kirchhoff's current law, which is that, the current going around this loop all has to be equal. That's the equivalent to constant charge, right? If your electron moves from here, the electron moves from there, the electron moves from there, the electron moving in a circle, and the current must be the same everywhere, right? So Kirchhoff's current law, Kirchhoff's voltage law, this is another way of saying conservation of charge and conservation of mass, I think was the other one.
Yeah,
It's just
conservation.
Yeah, there's conservation law. But but the other thing is that you have your device equations, right? So if you remember Ohm's law, right? So the resistor equation is the voltage of the resistor equals the current through the resistor times its resistance R. Right? That's the Ohm's law. And the other equation that you have is that the capacitance, the current of the capacitor is equal to the capacitance times the derivative of the voltage, right? So this is actually differential equation, right? This is where the differential equation comes from. That's the capacitance law, right? So these are our 4 equations. And how do we actually, at the end of the day, you want to take over equations and build an ODE system out of it, right? So how do you actually do causal modeling? Well, what you do in causal modeling is you actually go and derive what those equations are for you, right? Say, okay, here's my 4 equations. But what if you have the current to the capacitor is equal to the capacitance times the voltage of the capacitor. So my differential equation is VC is equal to this, but IC equals IR. IR equals, use Ohm's law, so that's IR is equal to VR divided by R, and then VR is equal to V minus VC. So I plug in here, and there you go. So the voltage of the capacitor is actually, it's a function of the voltage of the capacitor. But in order to actually get this equation, be able to relate, the derivative of VC back to its own current value, you actually have to go through a whole lot of steps, right? You have to do this out by hand, work this out, and when you actually are in the physics class, right? This is what you did, right? You write down your physical equation and you write it by hand, right? And now, if you want to work in a causal modeling environment, what you have to do is you have to say, this is the thing that I want to solve for. So let me build up the blocks for doing this. And if you've ever used Simulink before, you'll know what this looks like. If you've never used Simulink before, this will look weird as all heck. So what does this mean? Well, okay, so I have an integrator block, which what the integrator block does is it goes from the derivative expression to its value. So if I want to put into the integrator, I want to put into the integrator the expression for BC dot. Yeah, and that BC dot is equal to, what is VC dot equal to is 1 divided by RC times V minus VC, which is equal to, and so if I have a gain block, this 1 minus VC, and put V plus minus times VC, right? Because the integral of VC dot is equal to VC. So this line down here is minus VC, this thing here is V, and so this is a V minus VC divided by RC is equal to V dot. And if you've never done that before, that will look like complete, utter alien nonsense. But that's how causal models end up being built, right? But why, so this is a way of doing modeling, right? You can see here's ModelingToolkit building. So you can build causal models in the ModelingToolkit. But why might you not want to do this, right? Well, first of all, it might look a little bit nicer to just say, I have a resistor, a capacitor, voltage, and ground, and here I just connect these things. And this allows you to do the equivalent of these. This gives you the equivalent system that when you simulate it, you get the same values, right? But what is the true difference between a causal system and an acausal system? Well, the true difference is that if you notice what we did right here, we just did, again, a bunch of mathematical expressions. You're going to find out what actually is the OG that we're solving for, given our tools, right? And so the issue with causal modeling is that it requires that you do this by hand, right? And so if I then just did a very small difference, or I just say, let's just put a inductor inside our equations, right? That is an inductance equation, right? Simple, just one more equation, right? Well, it turns out that what happens is, you have to do this by hand again, right? You take all your equations. I'm not even going to write out the whole set of symbolic expressions because it would take more than a slide to be able to get to these, right? But, you could, in theory, take the equations that you have for the system, write out your equations, and then write out the way of doing this causal expression on it, right? But the thing that you notice is that you're actually writing code for the simplified version of the model. And the simplified version of the model does not necessarily have the same structures as the unsimplified version, right? So while at an unsimplified stat, this is just adding elements out of here. The equations that you get here, your capacitance equation has completely changed, right? Your capacitance equation is no longer a opposite of C. You've completely changed your underlying OEEs, and so that means your implementation of the simplified version is actually completely different. Whereas if you do, and so it turns out that actually creating this and actually trying to construct the causal version of the models using your gains and your integrators and your core causal components can be rather time consuming to do. Whereas if you change this, if you use an acausal modeling system, you literally just added in an inductor and you just change your connection equations a little bit, and ta-da, now you have the more general system, right? And so you can actually see here when you go through this that the difference between the RC circuit and the RLC circuit in a causal sense is not just like a one-line change. It's like a 11-line change just to be able to go from the first version to the second version, right? And again, the reason is because while the RC circuit and the RLC circuit are similar in form, their simplified equations that you get in the end are very different. And you can understand this because, so the whole way to understand this is that, the equation that you solve for can be very dependent on very small details. Just for example, if I say I have a constant voltage right here, well, if I have a constant voltage right here, then I know the voltage. So therefore I'm solving for the current. And I'm solving for the current, then that's one way of solving it, right? But if I then say, I have a constant current input, then a constant current input means I'm going to solve for the voltage. And solving for the voltage is a completely different set of equations than the equations for solving for the current. So saying one component in the simplified version of the model, well, in the simplified version of the model, one change of component can be completely different equations. But in the unsimplified version, they can be a very similar type of equations, right? And so what an acausal modeling system lets you do is it lets you just specify how the model works at a very high level, and then all of the way that you actually generate those differential equations is, well, I mean, why would you do this by hand? I literally just told you we have a symbolic modeling system that is able to do expression manipulation, right? So what it's doing under the hood is exactly all this kind of stuff for you, right? But that's still not a complete description, right? I'm still haven't actually told you how the acausal model works. So now let's go step by step into how the components are defined and what the things actually mean, right? So again, this is description of acausal modeling number 4, which I expect that you only feel like you understand it like 30% right now. So if you feel like you're only at 30%, that's where you should be, right? So okay, so what is it? How do these connections work? Well, it turns out that in every form of physics, you always have two types of variables, right? You have things that are equal and things that sum through. And so, what do I mean by that? Well, inside of our RC circuit, what you have voltage and you have current, right? And what happens when you connect to these two things, right? So let's say you have the electric connection right here between these two objects. What must be true at this point and this point? Well, if you make this connection, then what happens to be true is that the voltage at these 2 points has to be equal, right? Because the voltages will equalize pretty much instantly, right? So the voltages here are equal, but the sum of the currents has to be 0. You might think the sum of the currents is 0. Well, it's just a different way of saying something else, right? Which is that the current flowing out of here has to be equal to the current flowing into there, right? So the positive current here equals the negative current here. But the same thing as saying current 1 plus current 2 is equal to 0, right? So your currents sum to 0, but your voltages are made equal. And so that is a property that is conserved across all other Hamiltonian types of systems. So, for example, if you have a translational or you have a translational connection or you have a mechanical system, right? If you connect two things mechanically, right, then the forces have to be equal, right? Because whatever force I'm pushing on my hand here is also the force I'm pushing on here, right? But then then you also have your flow, which is in your velocity equations. You have, for temperature, right, or for heat, if you have two places in the space that are directly connected, then that means the heat, the temperature right there has to be equal at that junction point, right? but the heat flow from output from one has to be the heat flow into the other, right? So the sum of the heat flow has to equal 0. Turns out that you always have these two types of variables. You have variables that have this equality, and you have variables that have this summation property, right? It turns out that it's fundamental to physics, because if you think about your Hamiltonian system, right, when you say, oh, I have a Hamiltonian, and I have my P, and I have my Q, right, I have these two types of variables. It turns out that your P variables are your ones that always have this equality relationship. Your Q variables are actually the ones that have the summation of 0. Right? So anything that's a Hamiltonian system tends to have this property, right? So what we do with Acausal modeling is we build tools that make use of this property and then simplify it down. So now you should be feeling like you have a 40% understanding of Acausal modeling, right? So now let's actually look at let's actually build up the Acausal model step by step by step. And I'm going to explain each part of it. So now what I'm going to do is that instead of using the components from the standard library, I'm going to build all of the components from scratch so that you can see every single equation that shows up in our RC circuit, what it means, what it accounts for, and then we'll understand the entirety of this example, right? And man, that's a very bad spelling error I just saw right there. But okay, so first of all, what I'm going to do is I need to define my pin, right? So when I say I have this positive pin and I have a negative pin, right? What is a pin? What am I connecting? Well, a pin is this thing called a connector. So I'm going to define my pin connector as it has a voltage in there and it has a current in there. And the current is something that connects by flow, right? And what do I mean by that? Well, what I mean by this is, so this connector is something where when I make a connection equation, between two pins, a connection equation means that the voltages of these two pins are equal. And then the summation of the currents is equal to 0. Right? Again, that is a statement that anytime that you connect two these logic elements together, you always have to have the property that the voltages there are equal and the current sums 0. Right? There's two types of variables, and so connect equals flow. That is my way of specifying that the current equation is one of these flow type variables. Right? So that is how the pin is constructed. And so now what I do is I build these. When I'm building these Acausal models, I now build models of models. Using these components inside of it. So the first one, this easy one, is how was ground defined? Well, ground is a model, right? So I do add mtk model ground. Ground is a model that has a component in there. Ground is a model that has a component and it has a pin called G, right? So everything always has these components, and then you have the extra equations that go with it, right? And so what are the equations that go with ground? Well, by definition, what we always say is that the voltage of our ground is equal to 0. That's the definition that you always use in electrical circuits, right? So what we do is we just define the equation that is the voltage of our pin is equal to 0. Because I pulled it in from the standard library. Okay, so it's not letting is already defined in my thing, etc. So this is the set of equations. Okay, so that's all. So if you want to know what exactly is the ground component inside of the model library, it's literally just this: that you have a pin inside in there, and so it has a G dot voltage. It has two variables, right? A ground has a G dot voltage and it has a G dot current, and it also comes with the equation that G dot voltage equals to 0, right? It always specifies that equation.
It's also worth pointing out that the number of equations you're going to need each equal to the number of pins that are in the components, and all the other equations are going to come from the connections.
Yeah, exactly. Yeah, so the number of equations that you have are going to be equal to the number of pins, because then other equations that you'll get will come from the connection semantics, right? We'll show that expand out in a second. Yeah. I will not talk about stream connectors right now, but there are stream connectors in the library. So yeah. So you can do string connectors and all that, and they're basically putting that you have constant entropy that's for two-phase flows in HVAC systems, et cetera, et cetera. We do have it implemented, but it's definitely not an elementary thing to have in the first example. Yeah.
Like a capacitor that's
I'll get to that in a second. Yeah, well, let's build up the capacitor first. So the first thing is, so one of the things that is concerned here, so we have a lot of these things that have 2 pins in it, right? It turns out that for people who are electrical engineers, an electrical object that has 2 pins is called a one port. One port has a pair of pins. I don't like the naming, but it's a standard naming, so we use the standard naming. And so the general circuit component is something that has 2 pins in it, right? So let's create this general object of a 2-pin object, right? Which we call one port. So our one port object, and if you Wikipedia it, you'll see that this is a convention. It is weird. At components begin. So a one port is something that has a positive pin and it has a negative pin, right? And now it also has these variables, right? Because when we talk about, say the resistor, right? Then we say, oh, the voltage of the resistor, the current of the resistor, right? So for the resistor itself, there is a voltage and there is a current, right? So that means that there also needs to be some equations. At equations begin. What are the equations? Well, if you think about how would you, if you're actually to go and try to say, in your physics class, if you wanted to measure what is the voltage of the resistor, what would you do? Well, you would take, you get your voltage meter, right? You would put one piece of the voltage meter here, but the other voltage meter here, and you measure the voltage across the resistor. So the voltage of the resistor is defined as the voltage drop across it, right? So a one-port object, the voltage of an object is equal to the voltage drop across that object, right? And now, how do you define the current? Well, the current of the object is, you have to have the current flowing into it equals the current flowing out of it, right? So let's specify that has to be true, right? So the current, 0 is equal to the current flowing into the object is equal to the current flowing out of the object, right? I think I actually had a mistake in my notes there. I'll correct my notes in a little bit. Okay, so you have the current flowing into the object is equal to, actually no, there should be the sign. Yeah. Okay, yeah, because the current flowing out is the negative sign, right? So the directionality is positive or negative, right? So then how do you actually define the current of an object itself? Well, that is just the current flowing into the object, which is equal to the current of the current into the positive pin, right? So hopefully that made sense, right? So the voltage of an object is you put the pin here, you put the pin here, and the voltage drop across the object is the voltage of the object itself, right? And the current of the object is, well, the current flowing in has to be equal to the current flowing out. Observations of charge, electrons have to go somewhere, right? And so we're just going to define that the current of an object is the current that flows into, right? And that's your standard definitions from, you think back to the physics course, right? So this is just what your one-port object is, right? So a thing that has 2 pins is an object that is an object like this, right? And now, what is a resistor, right? Well, a resistor is an MTK model, right? A resistor is a model that it has as a component, or at extend. So we're going to use this extend macro, right? And so we're going to say this is a one-port, right? So a resistor is a one-port. So a resistor is a thing that has 2 pins where the voltage in its current is defined by these equations, right? But what is true about a resistor? Well, there's one other equation that we associate with the resistor, right? There's a parameter which is the resistance, right? And there is an equation with the resistor, which is the Ohm's law, right? V equals I times R. And if you think about it, what we just said is, okay, V is equal to voltage drop across the resistor is equal to I, which is the voltage current through the resistor, with times the resistance of the socket, right? But the current into the resistor is also equal to the current of the stand, and was equal to the opposite of the current of the stand. So actually, we really just define all of the relationships of the system. We now know from any voltage or any current, we now know how to calculate all these other voltages and currents within our resistor, right? We specified all these pieces, right? And so this is all we have to do for the other system. So at an MTK model, what is the capacitor, right? Well, you go over to Wikipedia and you check what is the capacitance equation, So what I'm showing here is, okay, what does that extend do? add extend is exactly the same thing as having written out your one port where you just add this one equation in here. It just is a nice way of doing inheritance, right? So extend is being able to extend a model is just a nice tool, but you could always write it out in full if you're, masochistic or something. So extend one port. So my capacitance equation, my capacitor is in the same thing, right? I just say parameters begin. I have a capacitance equation, and then I have my equations begin. D of V goes as I divided by C. This is just the capacitance equation, right? That the voltage of the capacitor is given by this derivative differential equation, D of V equals I divided by the capacitance. Okay.
Can I just make one comment of the side equation? So earlier you showed the equation that P dot I plus P dot N dot I equals 0. Just to be clear, the reason is because the side dimension is that current flowing into the component is positive. And that's important because it means it's non-directional. If you turn the resistor around, it still functions the same way. So the resistors and capacitors, you don't have to worry about how you connect, just like a real capacitor. But that's why it ended up being a plus.
Yeah.
This that also key the difference between plus and plus and only that the direction is not specified.
Yeah, the direction is not specified. So you could have switched around your positive and negative, and saying you still get you get effectively the same equations. You have different naming of things, right? But it doesn't actually matter what the directionality is. Its current can flow into the resistor one way, or it could flow the other way. It truly doesn't matter in the high level sense, right? Now, when you actually solve the system, right, it will then simplify the system down, and it'll find what the directionality of it. And so the simplification system actually generates a causal version of it. But you, as a high level user, don't need to know what necessarily the directionality will be, right? But then so then constant voltage is almost the same thing, right? It's just a component that has the voltage is equal to some, right? So there's not much else to that. And now, ta-da! That's the full definition of your RC circuit model, right? And then we just put all these pieces together, right? Now you should probably be at 50% understanding of it, right? Because now you know a little bit. Like, okay, these components. I understand. Ohm's law goes into here. I understand capacitor law goes in here. Well, how does this actually generate my equations in the end, right? Well, let's actually now look at it. Now let's actually look at all these equations, right? If we go back and look at it, it is just this whole list of the equations that we had, right? So here's the equations of the RC circuit, right? So if you actually go in there and kind of see now, okay, what is this equation right here? Well, this is the capacitance equation, right? That's the equation that we wrote inside the capacitor. That's the one with the capacitor. But what is this equation? Well, this is that the current of the source term is equal to the positive current here. Well, remember, right, when we define our one port, the definition of the current of the one port is just that the current of the one port is equal to the current coming into it. Now, if you go to each of these equations, see, it got the current in of the positive bit of the capacitor plus the negative bit of the capacitor equals 0. That's just the conservation of target equation, right? And so this whole list of equations, this is just all the equations that we just broke down in our components, right? Now, what do the connection equations do? Well, the connection equations, if we then call expand connections, right? If we then call this expand connections piece right here, you actually get all the different equations, and all that they do is they turn into the fact that if you anywhere where you put this, the two pins are connected, then you now have that the voltages are equal, and you now have that the voltages are equal at a connection. Let me see if I can find one very quickly. So the voltage of the source is equal to a voltage positive then on the resistor, right? So generated this equality relationship, but also for the flow variables, it has generated that the flow out of the source plus the flow into this resistor has to be equal. Okay. So you now understand every single equation in there. You can go to every single equation and say, where does this come from? Well, this comes from the one port equation that defines this, or where does this come from? Oh, it comes from our connection semantics. And we have 20 equations that all write this down. Right? And now this is your differential algebraic equation, right? All we did was we just said, these are all of the things that are true, right? These voltages are equal, these currents sum to 0. We just worked out everything that is true about the model. And then when we structurally and then we call simplify on it, and it finds your one differential equation, right? And that's how Acausal modeling works, right? Because behind the scenes, what it's doing, right? What it actually does behind the scenes is it does this whole process. It does the mathematics then for finding out like, oh, the ODE that you actually want to solve for is this one piece right here, right? So, but what you do is you just give it everything that's true about the model, and you have all these different variables, all these different equations, and it will find for you what is the optimal way how to solve this, and then it will solve the underlying equations, right? But the core about this too is that, again, we have all of this tooling in here. So for example, you have the symbolic indexing interface. So while you actually are solving for, RC model.capacitor.v, right? So while you actually solve for this variable, and when you plot it, this is what you get, you can actually ask it for any of the other variables. You can say, plot for, I want to use this as an index, I want to use the symbolic index. Well, what instead I want to do is give me the resistor, the currents of the resistor, right? And it'll tell you like, oh, here's the current of the resistor. Now, how does it know the current of the resistor? Well, it knows the current of the resistor because if you have the voltage of the capacitor, you figure out how it does this. I'm not going to figure out how to do this live, but it knows how to be able to give you any of the quantities from the system. And again, this is what your observed equations are, right? So you can check the observed of RC circuit. RC model, right? And you can see that it's actually generated all of these expressions, and it can know how on demand what the right order to recalculate them is in order to calculate the value that you're asking for, right? And so this is Acausal modeling, right? And so you can then see, your question back in the back there was, oh, so what if I want to do, let's say I want to have a variable resistor. So I want to have a resistor that is not ideal. Well, here you have your resistor equation, right? Well, you can make this equation be more complex, right? You just have a one port that is more complex. Now, what happens if you want it to be that heat dependent, right? Well, then it wouldn't just extend that one port because you'd also want to have, a heat port on there as well, right? So you say, oh, extend the one port, also extend the heat port, and now define the relationship of the resistance as a function of both the heat and the current. Right? And you just go on and on and on and on, and just build these more and more complex models. Now, the only thing that happens is that, you have to make sure that you only connect electrical pins to electrical pins. You connect your, heat pins to heat pins. But you have these different types of physical elements, and actually the compiler will enforce for you that you do this correctly, right? It's not going to just be insane. But you can define these models that say, oh, I have a battery. My battery has an electrochemical system, and so the electrochemical system of my battery, it has the battery itself has, if you think about the JuliaCon battery library, it has an entire partial differential equation that describes the electrochemistry of the battery. But then you can say, what is the voltage of the battery? What is the current of the battery? What is the temperature of the battery? Those are described for the battery. And so it just shows up as something that you can connect. And so you can then just, connect a real high fidelity, 1 million equation battery into your RC circuit. And now you have an extreme version of the RC circuit, right? But I mean, and that's how you start to build, more and more complex systems. You just start to put more and more physics into each of these elements. Yep.
My question would be, how does this play with the regular state that come from constant come from data?
Yeah, so the next question is, how does this play with equations of state that comes from data tables? So you can define, for example, interpolation objects that you can have as parameters. And so you can say, like instead of having a constant voltage here, like I have a voltage object that takes in a interpolation object, right? And then I'll just stick that interpolation in there. So there's a sample data components that let you do that. And there's all sorts of different components that then let you do these kinds of integrating data into your system. Yeah. Cool. So now you should probably be at like, say, 70%, 80% with Acausal modeling. You won't get to 100% just to watch right? Go back and actually build the components and work with it yourself. Once you actually go in there and check what all the equations are doing, then it will make complete sense of how I was able to do this derivation. Yeah.
Why this is a new kind of language, right? We define resistors out, it extend some things, in some things, basically, but we are very powerful. They need to
kind of types as you type hierarchies, but all with macros, and it also I feel makes it a bit more magical in a way. Maybe is there something we should add to the language, or that the language would need to do this less macro-y? Is this kind of a new kind of type something?
Well,
And did you think in a way?
I mean, you could do this completely without any macros, right? So one of these tutorials actually shows you this, right? Where if you just get rid of all these at name, right? You just undo like, name equals, right? This. So there's a tutorial that actually does this completely without any macros. The macros are just there to be able to automatically name objects for you and make things easier, quicker to build. But this is all just built in the Julia type system, right? So that way it can all be done, work with interactively. So for example, if you're writing a file reader, you don't want to use macros because you want to be able to directly build all the objects for you using the names that you create from the file.
But this SDK model is it and so on. It's a new kind of type.
Yeah, I mean, so MNTK model itself is almost like it's like a language, right? And we have to take this even further. So if you check out Mike's going to give a talk, I think tomorrow on the JuliaCon modeling language. It is a full modeling language that is defined on top of ModelingToolkit that is effectively competitor to the Modelica systems, which is a fully declarative language which lowers into ModelingToolkit, right? So ModelingToolkit then, I mean, this is a good question, right? Because ModelingToolkit lives in a very weird space, right? Because it is, in some sense, it is, you're using it into it. It is you're using it inside of the declarative programming language. But it is a declarative modeling tool. It is a declarative modeling tool that you are interacting with imperatively, which is actually very weird. I don't actually know of another system that is like that. And so you could do things like loop over models that you built, and loop over models, generate tons of different code, and say, for example, have a genetic algorithm that's giving you ODE systems in a loop, and then evaluating which of the ODE systems best matches your data, right? And so you're generating different types of equations, you're generating code, and so you're working with a declarative system interactively, imperatively. And that's a very deep topic, and especially you go to very deep into programming language discussion about what that means in terms of like the imperative declarative divide, right? Because, there are certain things in here that we're doing imperatively, certain things that declarative. I can show you how to work this whole spectrum within this one package. And so it is a weird entity. If you really think about what we just did here, it is very different, weird, and it's a very good discussion topic. Yeah.
It's about the change propagation in the articles or
can you use the modeling toolkit for in logical or probabilistic programs? I mean, you probably set up, so for example, in Catalyst, you have this other system that is a reaction system where everything is integer valued with a probabilistic representation, right? And then it has ways to be able to take a reaction system and lower that to an OD system or lower it to an SD system, and has similar connection semantics with inputs and outputs and all that, right? So you can define different types of systems and have different types of behaviors. So, for example, a Boolean, I know that some people in biological systems, they work on like Boolean logic systems, right? You could define a Boolean logic system that then lowers down to your integrator and such. So, I mean, we don't have that within base modeling toolkit, but there is an expansive set of different system types. And then people are building their own system types that are extending the library as well. So, this is not the full set of systems. So we do focus a lot on differential algebraic equations ourselves, but there's a whole world of things that can be mixed with this. In fact, one of the things that you can mix with ModelingToolkit is there's actually a state machine representation. So you can define state machines that are then mixed with your differential equations. And that's for things writing down things like control systems. Yeah.
I free comment a bit on the common places, although because that app brings up an external with probabilistic probability and things like that. But it's something that using what C2 does that this didn't really way in that.
General Hamiltonian system with probability
and share that. I will say, I mean, I don't know if Mike has a different opinion, but I will say that the Acausal versus causal naming has not grown with the science very well. I think that, I use the name Acausal modeling because that's what the whole ecosystem of Acausal modeling tools, that's what they've called themselves since the 80s. But I mean, I think that I would understand this. I mean, I don't know. I would always just say that it's just differential algebraic equation modeling in a general sense, right? So, but it's been called acausal modeling for so long that. But yeah, we talk about like causal modeling in machine learning. The causal modeling there has nothing to do with causal modeling here. Yeah. Let's go. All right.
I think that in many things that it does it both. But here's the game. Maybe he uses you initiate the first.
Yeah.
This is I think the main.
Yeah, and then so and then that's really the key, right? So acausal modeling, right? What we're really doing is we're just saying we just are writing down everything that's equal, right? This derivative is equal to this. This here is equal to this. These x plus y equals zero. We just write down everything that is true about that is equal, right? And then we use a symbolic system to be able to derive what is the right way to be able to solve this system of equalities, right? Oh, this is an ODE. Oh, this is a differential algebraic equation. Oh, it might just be a nonlinear system at the end of the day. There might be no differential. At the end of the day, the system here is really what it's really called. The acausal modeling system is the system that's all about, all of these things are equal. Find for me how to solve this equation. It's like, it's like a system of nonlinear equations. So it's an implicit system, right? Which is different from an explicit system where you have function, x is equal to f, y equals f of x, and then z equals, g of y, right? And where you have these explicit functions, you calculate one after the other, right? What you see is that, what you're doing in causal modeling is that you're finding out how do you calculate this variable given this one. If I know the voltage here, then I calculate the current here, starting to walk the equation, right? So causal modeling system, you just need to you have to write down all the steps of the calculation, whereas an acausal modeling system, you just say all the things are equal and it'll find the steps.
Yeah, I would say the distinction really comes from the fact that historically a lot of tools prescribe causality on all components, meaning they prescribe what was an input output on all components. And this is a way of distinguishing that mode, which is then called causal, from something else.
Yeah.
Which doesn't prescribe causality.
Mm-hmm. All right. So I don't know if we're going to get to the initialization in the end, but yeah.
Question. While some people working it, you said a couple times that this is all about Hierarchical systems. My question here is do you ever have stuff where it's this system has this energy fuse, and then you put those systems to look at how energy is conserved? Also, do you ever do symplectic integration?
Yeah. So do we do symplectic integration? Inside of the OD solvers, we have, a ton of symplectic integrators. And so I think we have 23 of them or something. Right? So you can do symplectic integration with the OD solvers, right? We don't actually have a way of targeting the symplectic integrators from the symbolic tools right now. That is a missing connection within there. There's reasons for that. But yeah, so you could, for example, say create a Hamiltonian system, right, where you give it your energy equation, and then it would know how to you need to say, okay, how do I generate an ODE system from that, right? You just differentiate with respect to that, you differentiate with respect to that. So you can create all these systems. I'm leaving that open because that's actually a great TSOT project, and so I haven't wanted to implement it yet. But it's also a great hackathon project. I think that you can probably create the Hamiltonian system or a Lagrangian system as a one-day hackathon project at the JuliaCon hackathon. So if you're interested in working on Modeling Toolkit, it'd be a great topic. But yeah, there's a lot of things like that, little physical things. And we do have a library, DiffyQ Physics, which is supposed to have some of these components, but it's a little bare right now. But again, I'm leaving it up for a student. Yeah.
And mostly then where you just solve the whole system.
Yeah.
Say, I know I've found that only will be interesting. It's this big part, this system that maybe a team be coupled to the holes. They're the way that's it high content.
Well, okay, so something I'll show a little bit of it because it does actually come into play in how the simplification occurs. But what it does in a simplification system is it has to find out what is the minimal set of states I need to solve for. And then I'll solve for things to get a complete view of the system, but it won't actually generate most of it, right? So again, it only solves one set of ODEs, which is the positive inner capacitor, and it will never actually calculate any of the equations unless you ask for their answer on the right? So that's the symbolic unit thing. So if you ask the solution, oh, what is the voltage rate here? They'll give you that, yeah, the voltage here is always 1 because it's constant voltage, right? But it will not actually create that array. It will never create that array under the hood unless you ask for it. So yeah, but it will find what is the minimal representation or minimal state of that system that is required for doing the bulk calculation. And that's pretty necessary because otherwise, you can't just say like, oh, if I don't know how this variable is defined and it's using another ODE, you have to have someone calculating it. So, yeah.
So my life worth I still use Modelica alt. We noticed that's not really useful for as you erase multiple similar components. At that point, this is the output you said that all the group that compares. Surrogates say that the quenching resistances and quenching capacitances, so exactly the same always with like that one, but just with different numbers.
Yeah, so the question here is about, how do you work with arrays, if you have these large, expensive components. Modelica, I think, has some kind of ergonomic stuff with that, right? So one of the things I want to mention is that, first of all, Modelica generates a full set of equations, like it unrolls all of these equations. And so as you get to very large systems, actually for this variable RC circuit, Demola actually crashes when you get to n equals 10,000. You just keep on going, right? So our code generator has a way to find loops. So the code generation on this is fast, and that's one aspect of the ergonomics, making sure to scale it. The other aspect of that ergonomics is the fact that, again, you have this mixture between it's embedded within Julia, and so you can use all of the Julia programming language features, right? So you can say, for example, you can use a comprehension of things to be able to create an array. You can use Julia's broadcast expression, so you can create a function where you just say, you create a function that is like f of xy is equal to, x is equal to y, right? And then you can do, f dot of capacitor, capacitor 1, capacitor 2, right? So you could basically use all of Julia's features for, doing linear algebra and array expressions and all this. You can do that on your symbolic components and generate equations like that. And so, there's a lot of very interesting things you can do, like, you can use a linear system to solve for your variables, and then put your solved variables into your equations and such. Which be very weird things to do within like a fully declared model within the Modelica environment, right? That does have trade-offs, right? Because that means that because we're building this imperatively, it might not be easy to understand. The only way to understand what all of your components are would be to run your code, right? Because you might have a while loop where inside of your while loop, you're iterating to tolerance for how many components you're going to have. So you could do really crazy things, but you do have the entirety of the Julia programming language for doing that. And so a lot of building very difficult models can be really nice in the system. In some cases where it's harder in Modelica. And in fact, Brad Hardman will be giving a talk on Julia Sim and why he used ModelingToolkit. This is one of the big reasons why he came to ModelingToolkit. He used a lot of Simscape before and ran into these ergonomic issues. Now, there is a trade-off there, right? Because we're doing this imperatively, there's not a direct Julia representation to ModelingToolkit itself, which is why we developed this Julia modeling language on top of ModelingToolkit. So that way there could be a layer that connects to graphical user interfaces. And again, Mike's talk will go to that in a lot more detail. So yeah, there's a lot of stuff. I mean, we probably see this at the Modelica conferences. We talk with the Modelica people a lot. And Mike has written a lot of the books on Modelica, right? So we know a lot of the stuff going on in Modelica. ModelingToolkit just sits in this weird space that's kind of Modelica-like, but interacted with in a way that is not declaratively building the declarative models, which makes some things easier, but it makes some other pieces difficult. So, and that's a much deeper discussion. You can talk a lot more detail. Yeah.
Well, that's nice. If one of the it's monthly. So that's it. What the mice put it works.
Yeah. So the question here for the audience here was, so let's say I have a non-symbolic function. So let's say I have a function that is a C call, right? Does the ModelingToolkit all still work for this? So what you have to do is you just have to be able to say, you have to be able to define a new coordinates. So what you do is you just say at register symbolic. And you just say, f of x, right? So let's say f of x is equal to, at C call, doing something weird, right? You just have to tell the system, the symbolic system, at register f of x. And when the symbolic system hits that equation, it'll just say represented as f of x. right? We won't trace into it. Now you might ask the question of how what's derivative, right? Well, when you register the function, you also tell it how it calculates derivative, right? You can say, oh, when you want to execute the derivative, you do this other C call, right? So you have to give this an estimation how to register it. But boom, once you've done a few registration functions, it now acts like any other built-in, right? In fact, all the built-ins, like how plus works, how multiply works, how sign works and all that, they've just registered functions using the same thing. Because again, everything's built in Julia, so you can add any function that you'd want the same way that the library has done. Yeah, but then that's a great question. Yeah.
If I listen with blocks or but
Yeah, so let me show you this live here, right? So x squared plus x, right? So normally if I just do x squared plus x, well, g of x equals x squared plus x, right? If I then call g of x on a symbolic variable, it'll trace into it, right? But if I do f of x and I register symbolic and I do f of x, it'll just represent it as f of x. It'll just say there's now this box where something goes on in here. But now what it will do though is when you actually do build function, when you build your function, right? If you have f of x defined in your system, then that function, the Julia function that you build, will then just call that Julia function for f of x when it needs to. So the function, all your code will still work and such, right? You're just black boxing it for the symbolic system, and then you have to tell it how to define its derivatives if it needs to differentiate it. But yeah, but again, every single thing that is in the symbolic library is just using the exact same symbolic registration. So all of the options that are available are also available to you to be able to define on your function as well. And so extending it for arbitrary functions. This is how, for example, people are integrating things with like refrigerant properties or cool property and all these other kind of property libraries for things like chemical processes and such. The only thing they need to do is you just have to register symbolic all of the calls to these property libraries. All right, cool. All right, now on to the last piece here, which is going to be, so now we got a feel of how do we build these causal and acausal models. Now I want to kind of go through understanding the power of structural simplification, right? Because what we get from acausal models is we now understand why everything is a differential algebraic equation, right? Everything in ModelingToolkit is a differential algebraic equation because in your components, you might write some differential equations, but you also have a ton of equality expressions that come from all these statements of the acausal model, right? This voltage equals this voltage, this current equals this current, right? All these equalities. And so your underlying system is always this differential algebraic equation. And so then the core of ModelingToolkit is representing differential algebraic equations and generating the best way to solve them.
as well as to regress and discrete statement and shred.
Yeah, there has been some progress on integrating discrete systems in with that. We have not done a webinar on it because we have not fully completed all of that yet. But you find Frederick, I think Frederick was we find Frederick, and Frederick is the one to talk to you about all these hybrid systems. What we currently have, we don't have everything with it done right now, but we have a lot of it. We also have completed the state machines. But right now, we can't put the state machine with the ODE problem. That's like 1 month away to need that. We're hoping to go something by JuliaCon, but we ended up kicking that beyond because we didn't have to talk about that part yet. But yeah, I mean, it is one of these topics of connecting all this together. Talk with Frederick on the current state of that. It is one of the things that we kind of showcasing in future versions of this. Sorry, on Pride. This talk on Pride. Okay. Yeah.
Uploadable connections that everything.
Yeah, you can create components all dynamically as well, right? These are all just Julia functions. So a component itself is just a Julia function. The macro is just creating a function. So you can create components using anonymous functions, and they're just the underlying tech is just an ODE system, right? So if you actually look at this other version of the RC circuit tutorial, it actually shows you a bit more of the underlying So basically
It's like.
Yeah. So an ODE system, so we always talk about like, when I started this discussion, right, I said, okay, create an ODE system and it's this thing with equations, right? But this hierarchical model is just an ODE system which has ODE systems inside of it, right? You can see right here. So it's just an ODE system which has a subsystems, which are all these other systems. You have systems of systems of systems of systems. Right? So it's actually just all represented within a type hierarchy. Yeah, it is. Effectively, it's a database of all of your equations and the relationships between your equations. Is there a way to add a delay? Yeah, yeah. So I mean, I did show at the very beginning here that I mentioned I wasn't going to show this in the talk in too much detail. If you instead of using ODE problem, you can use system yada. But you can for example, and let me blow this up so it's easy. See, you can for example say, instead of using x of t, I can use x of t minus tau, and you can have a delay differential equation. This is actually a stochastic delay differential equation. So that's delay in stochastic curve. So it shows you that it's more expressive than what I'm going to show, but that's because I'm simplifying it for this talk. Yeah. All right, cool. So now on to this last bit here, which is understanding difficult differential algebraic equations. So what is this structural simplification doing? And importantly, even if you're not building Acausal models and you're just doing differential algebraic equations, and you're user of SciML and you're just doing differential algebraic equations, why should you care about ModelingToolkit and this tooling for differential algebraic equations, right? Let's see if I can do the 15-minute version of this. So the test case that we're going to use is the Cartesian pendulum. And you might think at first, it's a pendulum. Okay, that's easy. So why would you use a pendulum? But I'm pretty sure that if you give me the 3-hour version of this, well, I ran a whole course where the only equation that we looked at was for a month was the Cartesian pendulum. So the Cartesian pendulum actually has a lot to it. I'm going to only talk about a very little part of it. So I'm going to start by, actually I've already imported all this stuff earlier, so let me start there. So let's actually just write down the Cartesian pendulum, right? So I have a parameter, g, and I'm just going to normalize gravity to 1. Let me restart my REPL because I already have a bunch of other junk in there. All right, so I'm going to grab all my things out of the library. I'm going to define my variables, add variables, x of t, y of t, and I'm not going to tell you what the state priority means right now. Hopefully I'll have time for that by the end. And t. What? Thank you. This is why Aisha is in the front row. Equations. D of x, right? So what are the harmonic oscillator equations? Is that the second derivative is equal to its value, right? And so what exactly is this lambda inside of here? Well, lambda is the tension, right? It's the tension on the rod. So it turns out that when you do your first physics class on the on harmonic oscillators and the pendulum, right? You make an assumption. You say if theta is sufficiently small, then sine of theta is equal to theta, and I get a linear ODE, right? Here, we're not saying sine of theta is equal to theta. There's actually, when you model the sloping out, there's a resistance on there, right? If you're interested, we can talk about this, but for now, I'm just going to write down the full set of equations due to time, right? But the key that you see here, right, which we want to get to, was the Cartesian pendulum is basically 3 equations, right? The second derivative in x is equal to a version of Fick's law with tension, right? Second derivative body is Fick's law of tension, but you also have gravity equal downwards, right? And you also have that x squared plus y squared equals 1, right? Because you have the pendulum on a rod, right? So there you go. This is a differential algebraic equation that has a constraint equation with 2 differential equations, right? But okay, well, you can't actually solve this though because ODE solvers want on first order system. But you'll notice something even weirder. So if you tell ModelingToolkit, if you go to ModelingToolkit and you say, hey, build this system, right? What you get from the pendulum system is you get this set of equations. You get, the derivative of y of t. You get some acceleration and the y t's. And then you have like 3 algebraic equations. It's most likely not what you expected. You've never seen a pendulum written like this, right? So where does this come from? Why is ModelingToolkit doing this? I'm trying to understand why ModelingToolkit is doing this. will help you understand why you want to use Modeling Toolkit for all of your differential algebraic equations. So, let's first build the system where we say, okay, let's do no simplification. And what we get from the no simplified version is we just get our three equations, det of dx dt equals z, ddt of dy dt equals z, and our constraint, right? It turns out that you can't actually solve that over ODE solvers because it doesn't know how to handle second order derivatives, right? So we need to turn our second order derivatives into first order derivatives. But there is a way to be able to do that. You can just call, ODE order lowering. And so there you go. So what does this mean? Well, it creates a new dummy variable, right? Active t, which is equal to dx dt. And so then the second derivative is dx of t dt, which is equal to, so you're just defining a new variable that is the derivative of the first variable. And then the derivative of the derivative is, well, that's the second derivative, right? And so that's if you've ever done a course on ODE solvers, they tell you like, oh, and here's how you lower your systems to first order. And while, ModelingToolkit has a function that will do that for you. Okay, that's not so impressive, but here you go. This is our Cartesian pendulum, right? So here's our Cartesian pendulum. We do ODE lower problem, right? We then build this ODE problem with a Cartesian pendulum, and then we solve it, and we immediately get a solver error. There you go. Well, that must be because Rodos IP, you're a terrible solver. What are you doing? Like, let me go to a different solver. So I go to a different solver, and I get another solver error. In fact, you get a solver error at exactly the same time point, or around the same time point in time. And it says that your system's unstable, and nothing works, right? So what happened? I mean, I thought that this is a perfectly reasonable set of equations. Why can't the solver solve it? My claim here is that the solvers actually did nothing wrong. It turns out that this actually just has a very adverse behavior. So this way of writing the equations has a very adverse behavior on the differential equation solvers themselves. And how can I find that? Well, I'm not going to do too much math here, but I always I can't resist ever. Right? So a little okay, so what's going on here? So let's say you have a differential equation, u prime equals f of u t. So then what you do is you say, okay, so the implicit Euler method, right, is equal to un plus 1 is equal to un plus delta t f of un. Now we're going to skip the other, right? Or f of un plus 1, right? So this is your implicit Euler method, right? And so the way that implicit Euler works is you move everything to one side. We have g of u's of f plus 1 is equal to un plus 1 minus un minus delta t f of u, right? Or what you can do if you have this as a matrix equation, then you have that g prime of un plus 1 is equal to I minus delta t times the Jacobian of f. Right? So that's very quick, but basically you have a Newton method inside of your ODE solver. Oh, Pax didn't hit it. It's back on. All right, cool. So this is very quickly written down. So if you look at your implicit Euler method, it's un plus 1 equals un plus delta t times f of un plus 1, right? And we have to make that split. Oh, yeah. I mean, yeah, so, I'm just going to give people introduction to the course, and I all join MIT. But then the Jacobian of the implicit Euler method is this I minus delta t times f, right? Well, it turns out that if you actually have a mass matrix here, because you're representing a different Greek equation, and you have your mass matrix right here, you have a mass matrix right here, and then this becomes your mass matrix, right? So, but okay, why does this matter? Well, let's just instead of calling this delta t and call this gamma, you end up having this as your Jacobian for all of your implicit solvers. So this is the Jacobian for all of our implicit solvers. Let's actually look at the Jacobian inside of the solver method, right? So inside of an ODE solver. Okay. So inside is an ODE solver. The way that we primary equations inside of the ODE solver, this is the Jacobian that is trying to use inside of its Newton method, right? And now if I compute the determinant of this, and this is my determinant, and I might ask, why do I care about the determinant? Well, let's ask the question. Well, here's the Jacobian, right? It's this I, and there's identity matrix. Well, there's the mass matrix, basically. I'm not going to explain that too much. I could go into detail later. Right? But this is basically my mass matrix minus gamma times this, where gamma is equal to delta t. This is the way plus the right method, or is a constant times delta t for any other method, right? And so what this means is as delta t goes to 0, what is my determinant of my Jacobian? It's 0. And so as delta t goes to 0, for the way that we define these equations, it turns out that the Newton method has a singular Jacobian, and so the implicit solver is not able to solve it. And in fact, as you decrease the dt in your ODE solver, you actually increase the error, and so the adaptivity algorithm will never actually be able to work because it's not conversing on the set of equations. So this looks like a very innocent thing. Again, it's just a pendulum, right? But here, with the way that I've written now the pendulum equations, it makes a whole lot of sense. But turns out that if you write pendulum equations like this, the ODE solvers will all fail. And this is not just a property of our ODE solvers. You can show this happens to the sundials of ODE solvers. This happens to all 410 ones. This is the internal property of the ODE solvers because the Jacobian has a singularity. And so therefore, the Newton method is not able to be solved. As delta t goes to 0, you actually do not decrease your error anymore because of that Jacobian. So how do you solve this? Well, it turns out that I, as a numerical method writer, I've been writing differential equations. I was writing it for 5 years. And when I ran into this problem, I realized there actually is nothing I can do as a numerical person to solve this. The problem is that you wrote down your equations. You have to change your equations if you're going to get rid of this issue. So what exactly is the issue? Can we understand when you will run into this issue? Well, let's look at our equations, right? If you look at our equation, let's then understand what is each equation telling me, right? So the first equation is telling me how x sub t evolves, right? The second equation is how y sub t evolves. Third equation is how x evolves. Fourth equation is how y evolves. The last equation is supposed to tell me how lambda evolves, right? How the tension evolves. But lambda doesn't actually show up in those equations at all. That's why you have this singularity in Jacobian, because this equation is supposed to solve for lambda, but lambda's not in that equation at all. So what do you have to do? Well, let's use symbolics, right? We have a symbolic library, so let's take our constraint equation and differentiate it once. So we differentiate we differentiate our constraint equation, and then we substitute in all of our values, and then this is the first derivative of our constraint equation, right? Well, that's not too interesting yet, but what happens if we differentiate the constraint equation one more time? If we differentiate the constraint equation one more time, we get this much larger expression, but if we then substitute everything in, we actually see that the second derivative of our constraint equation has lambda. And that is actually another constraint that our system needs to satisfy. Our system also needs to satisfy that 0 equals this expression. It is known as an implicit constraint inside of your differential algebraic equation system. And so what happens if we do this? What happens if you write down, your equation of our pendulum is equal to, ddt, dxt is equal. Everything's the same, but instead of writing our constraint as x squared plus y squared equals 1, we write our constraint as the second derivative of the substituting everything into that expression, right? Physically, this is the exact same physical equation, because if the first constraint is equal to 0, we should be able to differentiate it. Derivative is equal to 0. Its second derivative is equal to 0. So this is exactly the same physical system. But if I solve it, right, like the key here is that since lambda shows up in the system, the singularity in the ODE solver doesn't exist. So if I solve my pendulum, it works. Ta-da! So that's all you have to do, right? So if you write down a differential algebraic equation and the solver doesn't work, you just, instead of writing the equation that you had, you just write this one. Obvious, completely obvious, right? So this is why ModelingToolkit is, even if you're just, using differential equations.jl directly, and you're using differential algebraic equations, this is why it's useful, right? Because, this is actually a better way of solving that system. It is physically equivalent. But now, what happens is that if you give structural simplify the set of differential algebraic equations, it knows how to actually generate that form. It knows how to generate that form, right? Now, if you go back to the very top here, though, you'll notice if you go back to the very top here, you'll notice that it's, that is one way of solving those equations, but it didn't even generate that one, right? What you'll notice is that the last equation in here is that equation that we derived, right? But what are the other two equations in there doing? Well, what you actually see is that the first equation is an original constraint. The second one is the first derivative of our constraint. The third one is the third derivative of our constraint. So what it did was it created, following these two extra implicit constraints, actually deleted two of your differential equations, right? Because these other constraint equations are more information than that. So why did it do that instead? Well, it turns out that the system that we wrote down, this set of differential equations that we wrote down, they said, oh, this is our corrected version of it, right? Not only is it it is a corrected version of it. It makes the solver work by eliminating the singularity within the stepping behavior. But it turns out that it's actually, we only now impose that the second derivative of the conservation law is held, which means that the first derivative of the conservation law is not necessarily equal to 0, which means that x squared plus y squared is not necessarily equal to 0. So if we solve our equation over a very long, so if I solve the harmonic oscillator from a small time span, oh, hey, look, I get a harmonic oscillator, right? But if I solve it for a very long time span, if I just let it keep on going and going and going and going, what you can actually see is that that representation of the equations ends up allowing for numerical error in x squared plus y squared equals 1, and that numerical error can grow and it can actually drift, right? So how do you actually correct for that drift? This is something called the dummy derivative method, where these other constraints that you get in there during this differentiation process can be put in there. And so this is why then the version that ModelingToolkit constructs, it adds in these other two constraint equations, and then it has to know which other equations to delete. How does it know which other equations to delete? Well, it could either delete the x equations or the y equations. We told it with a state priority to prioritize keeping y instead of x. And that is why it kept the y equations instead of the x equations and deleted the differential equations for x. And this is the form that it chooses. And the form that it chooses here actually makes sure that x squared plus y squared always equals to 1. In fact, if we ask the solution for this observable, right, remember back to our symbolic indexing, x squared plus y squared always equals 1. So therefore, conclusion there is structural simplify is very smart. If you've ever met Yingbo Ma, he's a very smart dude, and he spends his entire day, the last 5 years, figuring out how to make differential algebraic equations work better, and structural simplify will do all these things automatically. So even if you don't use ModelingToolkit for, you can see how for Acausal modeling, you get a system that has all these equality equations, and it will do all the stuff behind the hood to be able to build one that's solvable. But even if you write a DAE yourself, ModelingToolkit will still be useful because of how this is working. And this then corresponds back to all these other questions. So you said, why might you want to do symbolic differentiation? Well, because this transformation right here is not something that you can do with automatic differentiation. We're only differentiating part of the equations and not other parts of them. So this requires symbolic differentiation. And you can see all the parts of symbolics involved in here because you can see how we're differentiating and substituting, and the whole symbolic system is coming into play here, right? So this really kind of completes the story of, what is ModelingToolkit? It's a system for modeling differential algebraic equations that lets you build these hierarchical models. They get gigantic differential algebraic equations and then turn it into something that the solver actually wants to see, because we're building the solvers to work with these representations, and it understands better than most people how you should write those equations so that way it's easy to solve, and then it solves it for you, and it gives you all the tools to map it back to the equations that you want. And that is ModelingToolkit, and that is why we have all this, so we worked for years on the differential equation solver, but this is why we've now added this whole symbolic layer to it. Thank you very much.